The universe contains mysteries far beyond imagination. From stars, planets, and galaxies to the intricate details of subatomic particles, there's so much we're still learning. Join us today as we delve into some of the biggest mysteries in the universe. The formation of black holes is primarily explained by a few key theories that revolve around the life cycle of massive stars and the dynamics of dense matter. One of the most widely accepted theories begins with the death of a massive star. When a star exhausts its nuclear fuel, it can no longer support itself against the pull of its own gravity. This leads to a catastrophic collapse of its core. As the core collapses, it can trigger a supernova explosion, ultimately shedding the outer layers and leaving behind a very dense remnant. If this remnant is sufficiently massive, specifically a few times the mass of our Sun, it can continue collapsing under its own gravity, leading to the creation of a black hole. This process effectively warps the fabric of space and time around the newly formed black hole, resulting in what is known as the event horizon, the point of no return for anything that ventures too close. Another theory involves the merging of neutron stars, or the rapid accumulation of mass onto an already dense object. When neutron stars collide, the gravitational forces can overcome any existing pressure from the particles within, leading to a black hole formation. Similarly, when a dense star like a neutron star accumulates enough matter from a companion star, it can surpass a critical threshold, causing it to collapse into a black hole. Additionally, there are theories suggesting the possibility of primordial black holes. These hypothetical black holes could have formed in the early universe through density fluctuations shortly after the Big Bang. They would not rely on massive stars, but rather emerge from the gravitational collapse of regions in the universe that had higher densities than their surroundings. These theories not only explain how black holes might form, but also highlight the diverse environments and conditions in the universe that give rise to these mysterious objects. Each type of black hole formation adds to our understanding of cosmic evolution and the intricate balance of forces that govern the universe. Supermassive black holes and stellar black holes are two types of black holes that differ significantly in their origins, sizes, and the roles they play in the universe. Stellar black holes form when massive stars reach the end of their life cycles. As they exhaust their nuclear fuel, they undergo a supernova explosion, leaving behind a dense core. If this core is massive enough, it collapses under its own gravity, creating a stellar black hole. These black holes typically contain several times the mass of our Sun, but are quite small compared to their supermassive counterparts. On the other hand, supermassive black holes reside at the centers of galaxies and can contain millions to billions of times the mass of the Sun. Their formation is still an area of active research. Scientists suggest they may have formed from the merging of many smaller black holes and massive gas clouds, accumulating so much mass that their gravitational influence becomes extraordinarily strong. One fascinating characteristic of supermassive black holes is their ability to significantly affect the galactic environment surrounding them. They can regulate star formation in their galaxies by emitting powerful jets and radiation as matter falls into them, influencing the behavior of stars and gas clouds. This interaction can shape the evolution of the entire galaxy over billions of years. While stellar black holes are small remnants of massive stars, supermassive black holes are colossal entities at the heart of galaxies, with complex histories that intertwine with the larger cosmic tapestry. Understanding these differences helps shed light on the structure and evolution of the universe itself. The event horizon is a crucial boundary surrounding a black hole, marking the point beyond which nothing can escape its gravitational pull, not even light. To grasp its significance, imagine standing at the edge of a cliff. Once you leap off, there's no turning back. Similarly, crossing the event horizon means you are entering a region where the gravitational force is so intense that escape becomes impossible. This boundary serves as a dividing line between the observable universe and the hidden depths of a black hole. For someone watching from a distance, if an object approaches the event horizon, it appears to slow down and eventually freeze in time, as light takes longer to escape the pull of gravity. This creates a fascinating illusion where the outside observer perceives events in slow motion, while the object falling in continues its journey into the black hole, unaware of the external observation. Understanding the event horizon is critical because it fundamentally changes our perceptions of space, time, and the laws that govern them. It raises profound questions about the nature of reality and the ultimate fate of matter and energy once they cross this threshold. Essentially, the event horizon acts as a gateway into a realm where conventional physics begins to break down, leading to potential discoveries about the universe's most enigmatic aspects and further insights into the fabric of space-time itself. Scientists have developed various methods to observe black holes and their profound effects on the surrounding space and matter, despite the challenges posed by their very nature. One of the primary techniques involves studying the light emitted by nearby stars and gas clouds. When matter spirals towards a black hole, it forms what is known as an accretion disk. This disk consists of superheated material that radiates intense energy, particularly in the form of X-rays. By using specialized telescopes that can detect these high-energy emissions, scientists can indirectly locate black holes and gain insights into their properties. Another significant observation comes from the gravitational influence black holes exert on their surroundings. When a black hole is part of a binary system, paired with a companion star, researchers can monitor how the companion star orbits around an unseen object. This behavior reveals the mass of the black hole, which, while invisible, manifests through the gravitational pull it exerts. Additionally, scientists have employed advanced techniques such as gravitational wave detection. When two black holes merge, they create ripples in the fabric of space-time, sending out waves of energy. These gravitational waves can be detected by instruments designed to observe tiny variations in distances caused by these cosmic events, providing essential data about the merging black holes and their characteristics. Furthermore, the Event Horizon Telescope has captured images demonstrating the shadows of black holes against the hot gas surrounding them. The first image of the black hole at the center of our galaxy showcases the stark contrast created between the black hole and its luminous backdrop, further illuminating how these celestial entities interact with their environment. Through these methods, scientists have pieced together a compelling picture of black holes, not as mere voids in space, but as powerful forces that influence the cosmic ballet of stars and matter surrounding them. Each observation continues to expand our understanding of these enigmatic phenomena, revealing their critical role in the evolution of galaxies and the universe itself. Hawking radiation is a remarkable concept that reveals a surprising connection between black holes and quantum mechanics. At first glance, black holes might seem like cosmic vacuums that consume everything, including light, creating the illusion that they can never release anything. However, Stephen Hawking proposed that black holes can actually emit radiation due to quantum effects near their event horizons. Picture the event horizon, the boundary of a black hole, as a vast cosmic sea. In the quantum world, where particles and energy behave in strange and unpredictable manners, there exist pairs of virtual particles that constantly pop in and out of existence. Normally, these pairs annihilate each other almost instantly, but right at the edge of a black hole, one of these particles might fall in while the other escapes. The escaping particle manifests as radiation, while the particle that falls into the black hole effectively reduces its mass. This fascinating process indicates that black holes are not entirely permanent fixtures of the universe. Over incredibly vast stretches of time, as they emit this radiation, black holes can lose their mass and energy. Imagine a candle slowly burning down as it consumes wax to stay alight. Gradually, the candle diminishes until it eventually extinguishes. Similarly, a black hole can gradually evaporate through Hawking radiation. The implication of this phenomenon is profound. It challenges our understanding of these enigmatic objects. If black holes can evaporate, it raises questions about what happens to the information that originally fell in. This concept of information loss is a significant puzzle in modern physics, leading to intense debates among scientists. Hawking radiation, therefore, holds the key not only to understanding how black holes might disappear, but also to unraveling the mysteries of the universe as a whole, blending the realms of gravity and quantum mechanics into a single narrative of cosmic evolution. The existence of dark matter is supported by several lines of compelling evidence. each contributing to a larger picture that scientists have been piecing together over decades. One of the most significant elements is the way galaxies rotate. Observations reveal that stars far from a galaxy's center move at speeds that would suggest the galaxy should break apart. However, they remain intact, indicating there must be unseen mass holding them together. This unseen mass is often attributed to dark matter. Another persuasive piece of evidence comes from gravitational lensing. When light from distant objects passes by massive celestial bodies, such as galaxy clusters, the light bends due to gravity in a phenomenon known as gravitational lensing. This bending provides a means of estimating the total mass of the foreground object. Scientists find that the visible matter alone cannot account for this effect, suggesting that a significant amount of unseen matter, dark matter, must be present to exert the necessary gravitational influence. Additionally, the cosmic microwave background, which is the afterglow of the Big Bang, shows slight fluctuations in temperature and density. These variations reveal insights into the distribution of matter throughout the early universe. The patterns observed align closely with predictions that include dark matter, as it plays a crucial role in the formation of large-scale structures in the universe. Lastly, numerical simulations that model the universe's formation and evolution consistently require dark matter to reproduce the observed structures we see today. These simulations show that without dark matter, galaxies and clusters would not form as they currently do. Through these diverse strands of evidence, galactic rotation, gravitational lensing, cosmic microwave background analysis, and simulations, scientists have built a strong case for the existence of dark matter, even as its true nature continues to elude full understanding. Dark energy acts as a driving force behind the universe's expansion, which has become increasingly evident as we study the cosmos. Imagine the universe as a balloon being inflated. As the balloon gets bigger, every point on its surface moves away from every other point. Similarly, the universe is stretching out, and this process is not slowing down, it is actually speeding up. Initially, after the Big Bang, the universe was in a state of rapid expansion due to the immense energy released during that event. As it expanded, gravity worked to pull everything back together. However, that gravitational pull is now being overcome by dark energy. This mysterious form of energy, which makes up a significant portion of the universe, exerts a sort of pressure that pushes outward. Scientists have observed this phenomenon through distant supernova, exploding stars that shine incredibly bright. By measuring their light, experts have determined that these supernovae are farther away than expected if the expansion was simply slowing down. Instead, the data indicate an accelerating expansion driven by dark energy. While dark energy remains largely an enigma, its effects are profound and pervasive. It affects galaxies and large-scale structures, influencing the very fabric of space-time. By understanding dark energy, we gain insights into the ultimate fate of the universe, which could include scenarios from endless expansion to a possible eventual reversal under gravity's influence. For now, dark energy continues to shape our universe, moving it toward a future where distances between galaxies grow ever larger. Detecting dark matter is one of the most challenging tasks in modern astrophysics, partly because it does not emit, absorb, or reflect light, making it invisible to traditional instruments. Scientists are employing several innovative methods to uncover its presence and properties. One primary approach is through gravitational effects. Dark matter's mass influences the movement of galaxies and galaxy clusters. For instance, scientists observe how fast stars orbit at the edges of galaxies. If only visible matter were present, these stars would be moving much slower than they actually are. The extra gravity indicating a significant mass, presumed to be dark matter, is inferred from these speed measurements. Another method involves particle detectors located deep underground or in remote locations, designed to catch rare interactions between dark matter particles and regular matter. These detectors are shielded from cosmic rays and other natural radiation to enhance their sensitivity. When a dark matter particle collides with a regular atom, the resulting energy might create a detectable signal. This process is often compared to trying to catch a fleeting glimpse of a shadow in the dark. Astronomers also utilize cosmic surveys to study the distribution of galaxies and the large-scale structure of the universe. The way galaxies cluster together can provide clues about dark matter's effects, revealing underlying gravitational influences that guide their formation. By mapping these structures and analyzing how light bends around massive objects, scientists can infer additional information about dark matter, since this bending, known as gravitational lensing, occurs due to the presence of mass, even if that mass is unseen. This includes conditions found in the early universe, helping scientists understand what to look for in both observational and experimental studies. Altogether, these methods form a multifaceted approach to uncovering the enigmatic nature of dark matter, piecing together a puzzle that is fundamental to our understanding of the cosmos. Dark matter and dark energy represent two of the most intriguing mysteries in the cosmos, fundamentally challenging our existing understanding of physics. To start with dark matter, while visible matter makes up the stars, planets, and galaxies we see, observations reveal that there is much more mass in the universe than what can be directly detected. This unseen mass, dark matter, affects the way galaxies rotate. They spin in ways that can't be explained solely by the gravity of the visible matter present. Imagine trying to spin a basketball. If it's heavier on one side, it will wobble in an unexpected manner. Similarly, galaxies exhibit behaviors suggesting their mass is distributed differently than what we can see, indicating the presence of dark matter. On the other hand, dark energy poses a different challenge. Rather than being a form of mass, dark energy is associated with the accelerating expansion of the universe. When we observe distant galaxies, they appear to be moving away from us at increasing speeds. This was a surprising discovery, as most expected the gravitational pull among galaxies would slow that expansion. Instead, dark energy acts like a force countering gravity, driving galaxies apart. Think of a balloon being inflated. As you blow into it, every point on the surface moves away from every other point. This illustrates how dark energy fills the vacuum of space, pushing ever outward. Together, dark matter and dark energy suggest that we do not have a complete understanding of the laws governing our universe. They imply that the universe is composed of nearly 95% of unknown entities that behave differently from anything we can observe directly. Current physical theories, including our understanding of gravity and fundamental forces, are being tested and challenged in light of these phenomena, leading scientists to seek answers that could reshape our grasp of the cosmos. This quest not only seeks to understand what dark matter and dark energy are, but also their implications for the entire framework of physics as we know it. Dark matter and dark energy are fundamental components of the universe, shaping its structure and influencing its ultimate fate. Dark matter, which makes up a significant portion of the universe's mass, acts like an invisible glue holding galaxies and galaxy clusters together. While we cannot see dark matter directly, its presence is inferred from the gravitational effects it has on visible matter. For instance, when astronomers observe how galaxies rotate, they notice that the outer stars orbit at speeds that suggest there is much more mass present than what we can see. This unseen mass, dark matter, helps maintain the cohesion of these cosmic structures. In contrast, dark energy is a mysterious force that appears to be driving the accelerated expansion of the universe. Imagine blowing up a balloon. As you blow air into it, the surface expands, and not just the balloons themselves, but also the space between them. Dark energy acts similarly, pushing galaxies away from each other and causing the fabric of space itself to stretch. Scientists theorize that dark energy constitutes a significant portion of the total energy density of the cosmos, suggesting that it plays a crucial role in determining how the universe evolves over time. Together, dark matter and dark energy influence the universe's grand narrative. While dark matter helps form and stabilize cosmic structures, dark energy dictates the pace of expansion. The interplay between these two elements is essential for understanding the universe's current state and predicting its future. Ultimately, if the dominance of dark energy continues, cosmologists suggest that the universe may continue expanding indefinitely, leading to a scenario known as the Big Freeze. In this scenario, galaxies move apart so significantly that over vast stretches of time, they will be isolated from one another, rendering the cosmos a dark, cold, and desolate place. Through exploring these enigmatic components, we are slowly piecing together the vast and intricate puzzle of our universe. The Big Bang theory is supported by several pivotal pieces of evidence that weave a compelling story about the universe's origin. One of the most significant pieces of evidence is the observation of cosmic microwave background radiation. Imagine standing in a vast dark room filled with a faint glow. This faint radiation is similar to what you would expect to be the leftover heat from the early universe, when it was incredibly hot and dense and has since cooled and spread out. Scientists discovered this radiation in the middle of the 20th century, and its uniformity across the sky supports the idea that the universe began in a highly energetic state. Another crucial aspect is the observed expansion of the universe. When astronomers look at distant galaxies, they notice that most are moving away from us. This observation led to the interpretation that the universe is continuously expanding, akin to a balloon being inflated. If you imagine tracing back the paths of these galaxies, you'd visualize them converging at a single point, suggesting that everything was once concentrated there, reinforcing the initial explosion of the Big Bang. Additionally, the abundance of light elements offers further validation. In the aftermath of the Big Bang, conditions allowed for the formation of small, simple atoms like hydrogen, helium, and traces of lithium. Scientists can calculate the predicted amounts of these elements based on Big Bang nucleosynthesis, which details how these light elements were formed during the early moments of the universe. When researchers measure the actual amounts present in the cosmos, they find a striking agreement, lending credence to the theory. Finally, large-scale structure observations provide insight into how galaxies and clusters formed. By studying the distribution of galaxies throughout the cosmos, scientists have gathered evidence that supports the framework established by the Big Bang theory, showing the growth of structures from tiny fluctuations in density during the universe's infancy. In weaving together cosmic microwave background radiation, the expansion of the universe, the ratios of light elements, and large-scale structures, each piece forms an integral part of the narrative illustrating the universe's birth and evolution through the lens of the Big Bang theory. The cosmic microwave background, often referred to as the CMB, is a remarkable remnant from the very early universe, a faint glow that fills the entirety of space. Imagine the universe as it was shortly after its birth, incredibly hot and dense. This glow represents the heat left over from that formative explosion known as the Big Bang. As the universe expanded, it cooled, and light was released, becoming the CMB we observe today, nearly 14 billion years later. When we examine this background radiation, it provides crucial insights into the conditions present when the universe was just a fraction of a second old. The CMB is remarkably uniform, but tiny variations in its temperature point to the density fluctuations that seeded the formation of galaxies and larger structures. By studying these variations, scientists can decipher patterns that inform us about the universe's rate of expansion, its overall composition, and even the fundamental physics that governed those early moments. Moreover, the CMB is a time capsule showcasing the universe at that pivotal phase when atoms first formed and light could travel freely through space. Analyzing its characteristics helps cosmologists test theories about the universe's evolution and its ultimate fate. The cosmic microwave background acts as the afterglow of creation, offering a clear link between the ancient hot state of the universe and the vast structured cosmos we inhabit today. Through this window into the past, we gain a deeper understanding of not just how the universe began, but also the intricate processes that shaped it over billions of years. Inflation theory proposes a rapid expansion of the universe occurring just after the Big Bang, a moment in cosmic history more than 13 billion years ago. Imagine the universe as a small, hot and dense balloon, nearly the size of a pinhead. In the tiniest fraction of a second after the Big Bang, that balloon began to inflate incredibly fast, expanding exponentially. This expansion isn't just a stretching of space, it creates the very fabric of the universe as we know it. During this brief inflationary period, the universe expanded from an almost incomprehensibly tiny size to about the size of a grapefruit. This event smoothed out any irregularities and inconsistencies, leading to a remarkably uniform universe in its early stages. As the universe quickly expanded, tiny fluctuations in energy densities formed, laying the groundwork for what would eventually become galaxies, stars, and the other large-scale structures we observe today. The connection between inflation theory and the early moments of the universe is crucial. It explains why the universe appears homogeneous on large scales, despite being filled with matter that somehow organized itself into complex structures. Without the inflationary phase, the universe might have developed differently, perhaps leading to uneven distributions of matter. In simple terms, inflation acts as a kind of cosmic reset button, ensuring a smoother starting point for the evolution of all the cosmic components we see across the universe now. The concept of the multiverse offers a fascinating extension to our understanding of the Big Bang, a theory that describes the origin of our universe. Traditionally, the Big Bang suggests that everything we know, space, time, and matter, began from an infinitely small point and has been expanding ever since. This gives us a dynamic understanding of our universe's history. However, when we consider the multiverse, we are prompted to expand our view beyond just our single universe. Imagining the multiverse means envisioning that our universe is just one of many, perhaps an infinite number, each having its own distinct properties and laws of physics. If we think of the Big Bang as the moment our universe came into existence, the multiverse theory suggests that similar events could be happening elsewhere. Other universes may have undergone their own Big Bang-like expansions, leading to varied outcomes. This presents an intriguing idea. While the laws of physics we observe govern our universe, different conditions in other universes could lead to completely different forms of existence, or even no existence at all. One way to grasp this is to think about bubbles in a vast ocean. Each bubble represents a universe, formed independently and existing alongside countless others. Some bubbles might be similar to ours, with similar forms of matter and laws of physics, while others could be radically different. Each bubble's formation might have been sparked by its unique circumstances during the cosmic inflation that followed the Big Bang. Thus, the multiverse not only raises profound questions about the nature of reality, but also redefines our understanding of creation itself. Ultimately, the multiverse theory invites us to unshackle our imagination from the confines of one universe. It opens a doorway to the possibility that our cosmic story is merely one chapter in an endless, complex narrative, reshaping our inquiry into the origins of everything we see around us. It poses the idea that our universe, while extraordinary, is part of something far grander, a tapestry woven from the threads of countless realities. The Big Bang marks the inception of our universe, a colossal explosion that birthed everything we see around us. Yet despite extensive research, numerous enigmas shroud this momentous event. One of the primary mysteries lies in the exact conditions present at the very moment of this explosion. Scientists theorize that the universe started from an extraordinarily hot and dense state, but the details of how that state transitioned into the universe as we know it remain elusive. Another captivating puzzle involves the cosmic inflation phenomenon. This theory suggests that incredibly rapid expansion occurred just after the Big Bang, making the universe larger than anything we can currently conceive in an incredibly brief time frame. However, what triggered this inflation and how it unfolded is still poorly understood, leaving researchers eager for answers. Moreover, the nature of dark matter and dark energy, which constitute much of the universe's total energy density, is still largely unknown. While theorists have constructed models to explain their existence, the specific roles they played in the aftermath of the Big Bang, as well as their relationship with regular matter, challenge our understanding. Additionally, the matter-antimatter asymmetry presents yet another conundrum. Theoretically, the Big Bang should have produced equal amounts of matter and antimatter. However, our universe predominantly contains matter, and the reason for this imbalance is a major topic of exploration. Finally, the formation of the first stars and galaxies remains an area ripe for investigation. The processes that led to that initial structure formation from a nearly uniform state are complex and not fully understood. Understanding how gas clumped together under gravity to form the rich tapestry of the cosmos that we observe today is essential for completing our narrative of the universe's birth. While the Big Bang provides a framework for understanding the universe's beginnings, it opens the door to profound questions and mysteries that scientists continue to explore, each with the potential to reshape our comprehension of everything. Scientists employ several innovative strategies to search for extraterrestrial life, exploring both our own solar system and distant exoplanets. One of the foremost methods focuses on the examination of planets and moons within our solar system. For instance, researchers are particularly intrigued by places like Mars, where past water activity suggests it may have once harbored life. Robotic missions equipped with specialized instruments scavenge the surface and analyze soil and atmospheric samples for signs of organic compounds, the building blocks of life. Beyond Mars, icy moons such as Europa and Enceladus capture attention due to their subsurface oceans, hidden beneath thick layers of ice. By sending spacecraft that can penetrate these icy shells, scientists aim to sample the water beneath, searching for microbial life or the chemical cues that life may leave behind. Another exciting avenue is the detection of exoplanets, worlds orbiting distant stars. Utilizing space telescopes, scientists survey the atmospheres of these planets when they transit in front of their host stars. By analyzing the light that filters through a planet's atmosphere, they can identify gases that could indicate biological processes, such as oxygen or methane, which, in combination, might hint at life. Additionally, the search for technosignatures plays a critical role in this quest. This involves monitoring radio signals and other emissions from space, looking for patterns that might suggest intelligent sources. Projects like SETI, the search for extraterrestrial intelligence, dedicate substantial efforts to this analysis, scanning the cosmos for anything that deviates from the natural background noise of the universe. Lastly, integration of artificial intelligence enhances these approaches by analyzing vast amounts of data from telescopes and space missions, allowing faster identification of potential signs of life. By combining these methodologies, scientists are steadily piecing together the puzzle of whether we are alone in the universe, expanding our understanding of life as we know it, and possibly as it might exist beyond Earth. Extremophiles are remarkable organisms that thrive in some of the harshest environments on Earth, such as deep-sea hydrothermal vents, acidic hot springs, and frozen tundras. By studying these resilient life forms, scientists gain invaluable insights into the potential for life in similar extreme conditions elsewhere in the universe. For instance, the existence of extremophiles suggests that life might not be confined to the familiar environments we typically associate with habitability, like Earth's temperate regions. Instead, it opens up the possibility that life could flourish on celestial bodies with extreme temperatures, high radiation levels, or highly acidic conditions. Places like Europa, one of Jupiter's moons, which has a subsurface ocean beneath a thick layer of ice, or Mars, with its ancient riverbeds and current frigid conditions, become exciting candidates for exploration because of extremophiles' adaptability. Moreover, understanding how extremophiles extract energy and thrive in environments devoid of sunlight encourages scientists to rethink what constitutes a habitable environment. This includes examining energetic sources that do not rely on the sun, thus expanding the list of potential ecosystems beyond those reliant on photosynthesis. Extremophiles serve as a biological blueprint, showcasing life's adaptability and resilience, encouraging researchers to search for signs of life in unexpected places. Their existence reassures us that life might find a way, and every exploration mission to distant planets could yield discoveries of organisms that reflect this extraordinary tenacity. The discovery of exoplanets situated in habitable zones has opened up thrilling possibilities for understanding life beyond Earth. A habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. This is significant because water is essential for life as we know it. Finding exoplanets within this zone suggests that there could be environments where conditions are suitable for life to evolve. Each new discovery expands our knowledge of the types of planetary systems that exist and demonstrates that our universe can host a greater diversity of worlds than previously imagined. Moreover, studying these exoplanets provides insights into their atmospheres and surface conditions. Scientists can examine whether they possess essential elements or chemicals like carbon dioxide, nitrogen, or even organic molecules, which are all crucial markers for the potential of life. The importance of these findings goes beyond simply looking for life. They challenge our understanding of how life might arise in different environments. They encourage scientists to question where life could exist in unconventional places, driven by various factors beyond those found on Earth. As our technology improves, we can gather even more data, allowing us to refine our theories about the likelihood of life elsewhere. Ultimately, each exoplanet located in a habitable zone contributes to a much larger narrative of cosmic exploration, inspiring curiosity about our place in the universe and igniting hope for the discovery of extraterrestrial life. Life on other planets could take forms and characteristics that are vastly different from what we experience on Earth. One of the fundamental aspects that may vary is how organisms obtain energy. On Earth, most life relies on sunlight, converting it through processes like photosynthesis. However, in environments with minimal sunlight, such as deep beneath the ice of Europa, life could emerge that relies instead on chemical reactions, perhaps breathing substances like hydrogen sulfide, which is found near deep-sea hydrothermal vents. The building blocks of life could also differ dramatically. While earthly life is primarily carbon-based, other planets with different elemental compositions might host life forms built on alternative chemistries like silicon. This could result in organisms with physical structures unlike anything we see here, possibly even extending to methods of reproduction and communication that are foreign to our understanding. Environmental conditions, such as gravity and atmospheric composition, would further influence how life evolves. An organism on a planet with higher gravity might develop more robust structures to support its weight, while those in a thick atmosphere with high pressure could adapt respiratory systems far different from our own. In a world where temperatures are extreme, either scorching or freezing, life might employ unique biochemical strategies to survive, such as antifreeze-like proteins to endure frigid conditions or heat-resistant enzymes for extreme warmth. Bioluminescence, which is limited to a few species on Earth, could become a common adaptation on a planet where sunlight is scarce or blocked by dense clouds. The ways life interacts with its environment through senses could also vary. For example, species might evolve to use echolocation or other methods akin to sonar, especially in environments where visibility is low. While the idea of life beyond Earth often invokes images of familiar creatures, the realities of alien life could be beyond our current imagination, shaped by different planetary conditions and elemental compositions. Each potential ecosystem harbors its own evolutionary pathways, leading to unique forms of existence that diverge significantly from our own life on Earth. Discovering microbial life on Mars or any other celestial body would have profound implications for our understanding of life and the universe. First and foremost, it would fundamentally challenge our perspective on humanity's place within the cosmos. The realization that we are not alone, that life might exist elsewhere, would enrich our comprehension of biology and the conditions that foster life. Finding extraterrestrial microbes would suggest that the emergence of life is not a uniquely earthly phenomenon, but rather a process that could occur under similar conditions in various environments across the universe. It would imply that various celestial bodies that were once thought to be lifeless, such as moons and planets within our solar system and beyond, could potentially harbor living organisms. Moreover, the investigation of Martian or extraterrestrial microbes could yield invaluable insights into the adaptability of life. Researchers would explore how these organisms survive in extreme conditions, environments with harsh radiation, low temperatures, and scarce resources. This knowledge might not only help us understand life's resilience, but could also inform us about potential biotechnological applications on Earth. Additionally, this finding would ignite philosophical and ethical discussions regarding the protection of extraterrestrial life, inspiring new considerations for planetary protection. As we contemplate the implications of discovering life elsewhere, we would also need to grapple with the responsibility of ensuring that our explorations do not jeopardize these ecosystems. Lastly, if we can establish that life exists beyond Earth, it would push the boundaries of scientific inquiry, leading to advancements in technology and methods for future explorations across the solar system and beyond. The quest for understanding life's origins and its variations would become a unified mission, encouraging international collaboration in space science. Each of these factors intertwines, highlighting how such a discovery could reshape our trajectory as a species, reshaping not just science, but also our culture and philosophy. The Milky Way galaxy, a stunning spiral galaxy, is structured like a flattened disk with a bulging center. Its shape resembles a spiral pinwheel, with arms extending outward like outstretched fingers. These spiral arms are rich in stars, gas, and dust, serving as the cradle for new star formation. At the heart of this galaxy lies a supermassive black hole, an invisible force pulling everything toward it with its formidable gravitational grasp. Our solar system is situated in one of these spiral arms, specifically within a region known as the Orion Arm, which is a minor arm located between two larger structures, the Perseus Arm and the Sagittarius Arm. Imagine the Milky Way as a vast, three-dimensional cosmic map, where our solar system occupies a position about 2/3 of the way out from the center. This places us approximately 27,000 light-years from the galactic core, nestled within a realm that is rich with stars, planetary systems, and interstellar material. The Milky Way is not static. It is a dynamic environment, constantly evolving as stars are born, live their lives, and ultimately die, often forming new cosmic structures in the process. As we contemplate our place in this grand galactic setting, we are part of a vast and complex ecosystem of celestial bodies, each contributing to the beauty and grandeur of the universe around us. Spiral arms are one of the most striking features of spiral galaxies and are formed through a fascinating interplay of gravity, motion, and the characteristics of the galaxy's material. To understand how they come about, imagine a vast collection of stars, gas, and dust swirling together in a galaxy, all influenced by their mutual gravitational attraction. As this material moves, it doesn't flow uniformly. Instead, it encounters regions of varying density. Think of it like a traffic jam where cars bunch up together. In a galaxy, areas where stars and gas are more densely packed interact with one another through gravitational pull, leading to the formation of spiral structures. This happens over time, as the galaxy spins, causing the denser regions to become aligned into beautiful, sweeping arms. These arms are significant for several reasons. Firstly, they play a crucial role in star formation. The gas and dust in the arms are often compressed due to the gravitational interactions, leading to higher densities in those areas. Under the right conditions, this compression allows stars to ignite into existence, effectively making spiral arms fertile ground for new star creation. Moreover, spiral arms also provide insight into the dynamic processes within galaxies. They serve as tracers of the galaxy's rotation and help astronomers understand the distribution of matter. By studying the light emitted from different stars within the arms, scientists can learn about the age and composition of those stars, revealing the history of the galaxy's development. Spiral arms are not just beautiful patterns in the night sky. They are the result of intricate cosmic mechanics and play an essential role in the life cycle of galaxies, sustaining star formation and illuminating the vast histories of these cosmic communities. At the heart of our galaxy lies a supermassive black hole known as Sagittarius, a star, captivating scientists and enthusiasts alike with its enigmatic presence. This black hole, millions of times more massive than our Sun, is shrouded in mysteries that spark intrigue and research. One compelling mystery is how such a massive black hole formed. Theories suggest it could have arisen from the merging of smaller black holes, or that it may have grown by accumulating vast amounts of gas and stars over billions of years. Understanding its origins not only provides insight into the evolution of our galaxy, but also into the life cycle of galaxies themselves. Another fascinating aspect is the behavior of stars and gas swirling around Sagittarius A star. Astronomers observe stars orbiting the black hole at astonishing speeds, revealing how strong its gravitational pull is. Studying these orbits allows scientists to map the mass of the black hole, but the dynamics of these stellar movements remain a puzzle. What factors influence their paths, and how do their interactions change our understanding of gravity? Additionally, there are tantalizing questions about the black hole's activity. While it seems relatively quiet compared to others in the universe, intermittent flares of energy suggest that matter occasionally falls into it. What triggers these events? The release of energy during these moments hints at processes we are still trying to fully understand. Then, there's the challenge of observing this black hole. Enveloped in clouds of gas and dust, Sagittarius A star is hidden from view in many wavelengths of light. Scientists must employ advanced techniques and tools such as radio waves to pierce this veil and gather data. Every new piece of information unravels another layer of complexity surrounding its nature. Lastly, the relationship between Sagittarius A star and the Milky Way is another enigma. The black hole's influence extends beyond its immediate vicinity, shaping the dynamics of our galaxy over cosmic timescales. What are the implications of this connection for star formation, galactic structure, and the future of our own solar system? These mysteries not only deepen our understanding of black holes, but also illuminate the broader workings of the universe. Each discovery leads to new questions, keeping the quest for knowledge alive and inspiring future generations of astronomers. The story of the Milky Way's formation and evolution is one of cosmic evolution that spans billions of years. Our galaxy began as small pockets of gas and dust in the early universe. Over time, these regions collapsed under the force of gravity, forming the first stars and clusters. Picture a gentle snowball effect. As more and more material gathered, the process accelerated, leading to the formation of larger structures. As these early stars burned out, they exploded in violent supernova, enriching the surrounding gas with heavier elements. These elements are the building blocks for new stars and planets, creating a cycle of birth, death, and rebirth that continues even today. Scientists believe that our galaxy underwent several significant mergers with smaller galaxies during its early history, events that shaped its spiral structure and gravitational dynamics. The Milky Way's disk is a stellar nursery, where new stars are continually forming from the remnants of ancient stars. As stars live out their life cycles, they influence the dynamics of the galaxy, triggering new bursts of star formation and contributing to the overall structure through phenomena like supernova explosions and stellar winds. We also know that the Milky Way is not a static entity. It continues to evolve even now, slowly merging with nearby galaxies, such as the large and small Magellanic Clouds. This ongoing interaction creates tidal forces that can trigger new star formation and alter the orbits of stars and gas in the galaxy. Diving deeper, astronomers have turned to advanced telescopes and computer simulations to understand the dark matter halo surrounding the Milky Way. This invisible substance makes up a significant portion of the galaxy's mass and plays a crucial role in keeping stars and gas bound together through its gravitational influence. The Milky Way's formation is a remarkable testament to the universe's capacity for complexity. From its humble beginnings as simple gas clouds to a dynamic and ever-evolving spiral galaxy, we learn how interconnected processes shape not just our home galaxy, but the greater cosmos as well. The Milky Way is a living example of cosmic evolution and a reminder of the fascinating journey that galaxies embark on throughout the eons. The Orion Arm is a fascinating region of our galaxy that helps illuminate our understanding of the Milky Way and our place within it. This particular spiral arm is home to many stars, nebulae, and other celestial features, which offer us crucial insights into the structure and composition of our galactic neighborhood. By studying the Orion Arm, astronomers can observe how stars are born and evolve within a region that is approximately 1,000 light-years wide. This area includes significant formations like the Orion Nebula, a nursery for new stars, where clouds of gas and dust coalesce under gravity to ignite nuclear fusion. Understanding the processes that occur here allows scientists to form models that explain star formation throughout the galaxy. Additionally, the Orion Arm is populated with familiar stars such as Betelgeuse and Rigel, which not only enrich our night sky but also serve as important reference points for mapping star distances and movements. Through comparative studies of these stars, researchers can uncover the dynamics of stellar motion, giving us insights into how our solar system, located within this arm, interacts with its stellar neighbors. Moreover, this region offers a glimpse into the cosmic web, the large-scale structure of the universe, as it looks revealing patterns across space. The Orion Arm is not an isolated section. It is part of a network of arms and regions, and studying it helps astronomers understand how mass is distributed across the galaxy, influencing gravitational effects and the movement of galaxies. Regions like the Orion Arm act as a cosmic classroom, teaching us about the life cycle of stars, the dynamic processes of our galaxy, and the connections that bind different parts of the universe. By piecing together this celestial puzzle, we deepen our understanding of not just our local surroundings, but also the grander structure and history of the cosmos. Neutron stars are extraordinary remnants of massive stars that have undergone a supernova explosion, the dramatic final act of a star's life cycle. To visualize this, imagine a star that is significantly larger than our Sun. As such a star exhausts its nuclear fuel, it can no longer support its own weight against the immense gravitational force trying to collapse it. When this balance fails, the core crumbles under pressure. As the core collapses, protons and electrons combine to form neutrons, resulting in a sea of densely packed neutrons. This forms a neutron star, which is astonishingly compact. In fact, a neutron star packs more mass than our Sun into a sphere no larger than a city, making it incredibly dense, so dense that just a spoonful of its material would weigh as much as an entire mountain. The onset of this process also leads to a striking feature. The supernova explosion blasts away the outer layers of the star, scattering elements into space and potentially giving rise to new stars and planets. The neutron star itself is typically left spinning rapidly and possesses a powerful magnetic field, which can lead to the emission of beams of radiation. If these beams point toward Earth, we detect them as pulsars, neutron stars that regularly pulse with radiation, like cosmic lighthouses. Neutron stars encapsulate the remnants of a massive star's life, marking a beautiful yet stark transition within the universe, where colossal forces collide and create some of the most extreme objects known to science. Pulsars are fascinating celestial objects that serve as natural laboratories for studying neutron stars and broader cosmic phenomena. At their core, pulsars are highly magnetized rotating neutron stars that emit beams of electromagnetic radiation outwards. As these beams sweep across Earth, much like a lighthouse beacon, they create regular pulses of radio waves or other types of radiation that we can detect. The significance of pulsars for astronomers lies in their extreme density and gravitational environment. Neutron stars, the remnants of massive stars that have undergone supernova explosions, are incredibly compact, with a mass greater than that of our Sun compressed into a sphere with a diameter of only about 20 kilometers. This unique combination of density and gravity allows astronomers to probe the fundamental laws of physics in ways that are impossible elsewhere. By studying the timing of the pulses emitted by pulsars, scientists can glean a wealth of information about their properties and the environments around them. For instance, variations in pulse timing can indicate the presence of gravitational forces acting on the pulsar, which can hint at the presence of nearby companion stars or other celestial bodies. This helps astronomers understand binary systems, where two stars orbiting each other can be studied using these pulse patterns. Moreover, pulsars are incredibly precise timekeepers. Their regular pulse intervals can rival the accuracy of atomic clocks, allowing scientists to investigate the fabric of space-time itself. For example, when pulsars are part of a system known as a millisecond pulsar, their spin rates can provide insights into how matter behaves under extreme conditions, furthering our understanding of fundamental physics, including the workings of gravity and the strong force that binds atomic nuclei. Additionally, astronomers use pulsars as cosmic reference points, helping to map the universe. The information gathered from pulsar signals can enhance our knowledge of cosmic distances and the large-scale structure of the cosmos. By analyzing the dispersion of signals as they travel through space, scientists can also see how interstellar matter influences their journey, thus providing clues about the composition of our galaxy. Pulsars are not just stellar remnants. They are key tools that help unravel the mysteries of neutron stars and the universe, allowing us to explore phenomena that push the boundaries of our understanding of physics and the cosmos itself. Magnetars are a fascinating type of neutron star, known for their incredibly strong magnetic fields, which are among the most powerful in the universe. Picture a neutron star, which is the remnant core of a massive star that has exploded in a supernova. A typical neutron star is already incredibly dense, with a mass greater than that of the Sun compressed into a sphere only a few miles across. Now, when this stellar remnant has a magnetic field, it tends to be immensely strong, but a magnetar takes this to an astonishing level. The magnetic field of a magnetar can be 1,000 trillion times stronger than that of Earth. To put that into perspective, just being close to a magnetar could strip away electronics or even distort the structure of nearby objects. These magnetic forces can release bursts of energy so intense that they can outshine entire galaxies for brief moments. When magnetars experience these explosive events, they release vast amounts of energy in the form of gamma rays and X-rays, making them detectable across great distances. What makes magnetars extreme goes beyond their magnetic fields. Their surface temperature can be incredibly high, and they often emit high-energy radiation. This combination of extreme magnetism and radiation makes them a unique subject of study in astrophysics, as they challenge our understanding of fundamental physics. The energy they generate, coupled with their short-lived outbursts, provides valuable insights into the life cycles of stars and the behaviors of matter under the influence of extreme conditions. Simply put, magnetas serve as cosmic laboratories for exploring some of the universe's most powerful forces. Neutron stars are among the universe's most extraordinary objects, presenting a unique challenge to our understanding of matter and the laws of physics. Imagine a star that has collapsed under its own gravity, compressing its mass into an incredibly small volume, causing a transformation that reshapes the very essence of matter. When a massive star exhausts its nuclear fuel, it can go through a supernova explosion, leaving behind a dense core, a neutron star. These remnants possess a density so extreme that a small sugar cube-sized amount of neutron star material would weigh as much as several 100 million elephants. This incredible density occurs because the core's protons and electrons merge to form neutrons, creating a sea of tightly packed neutrons held together by an intense gravitational force. Here, the typical behavior of atoms dissolves, and the established rules of physics, particularly those regarding nuclear behavior, are pushed to their limits. In such a compact environment, the forces at play are remarkable. The strong nuclear force, which usually binds protons and neutrons together, is stretched to its maximum capabilities, while the gravitational forces are relentless. This combination creates an environment where traditional physics begins to falter. For example, scientists grapple with questions about what happens at the very center of a neutron star, where densities and pressures exceed anything found on Earth. Could new states of matter exist there, possibly including quark-gluon plasma, a state where quarks are free from the neutrons and protons? Moreover, neutron stars can rotate at astonishing speeds, sometimes making several rotations per second. This rapid spinning can generate intense magnetic fields, leading to pulsars, beacons of radio waves emitted from these stars. This rotational behavior challenges existing physics principles, inviting researchers to rethink our understanding about energy, momentum, and the fundamental aspects driving the universe. All these characteristics make neutron stars not only a gateway to explore the fundamental nature of matter, but also a laboratory for testing the limits of current physical theories, such as relativity and quantum mechanics. As scientists study neutron stars, they continue to delve deeper into the mysteries of the universe, posing new questions that might redefine our comprehension of reality itself. Neutron stars are remarkable remnants of massive stars that have undergone supernova explosions. When a giant star reaches the end of its life, it exhausts the nuclear fuel in its core, which leads to a dramatic collapse. This collapse compresses the core to such an extreme density that protons and electrons combine to form neutrons, resulting in a neutron star, a stellar body so compact that a sugar cube-sized amount of its material would weigh as much as a mountain. In the cosmic life cycle, neutron stars signify a transition from the life of a star to the eventual fate of stellar remnants. They serve as essential indicators of the processes that govern stellar evolution. When a neutron star is part of a binary system, it can pull material from its companion star, forming an accretion disk. This process can lead to powerful bursts of radiation, and sometimes the phenomena known as X-ray binaries. Moreover, neutron stars are instrumental in cosmic events called gamma-ray bursts, which are among the universe's most energetic explosions. If two neutron stars collide, they can create a heavier element and emit intense beams of gamma radiation, a process that contributes to the creation of heavy elements like gold and platinum in the universe. These collisions also produce gravitational waves, which have been detected by observatories on Earth, revealing the cataclysmic nature of these cosmic events. Neutron stars are not only fascinating objects in their own right, but they also play a crucial role in the dynamics of the universe. They are key players in the recycling of cosmic materials and the ongoing evolution of galaxies, ultimately influencing the formation of new stars and planetary systems. Through their life cycle and interactions, these stellar remnants help shape the very fabric of the cosmos, making their study vital to our understanding of the universe. Gravitational waves are ripples in the fabric of space-time caused by some of the universe's most violent and energetic processes, such as the collision of two black holes or the merging of neutron stars. To visualize this, imagine dropping a stone into a still pond. The water's surface creates waves that radiate outward from the point of impact. Similarly, when massive objects accelerate, they create disturbances in space-time that propagate outward at the speed of light. The first detection of gravitational waves occurred in 2015, marking a monumental moment in physics. Researchers at the LIGO, or Laser Interferometer Gravitational Wave Observatory, utilized two enormous detectors located in different parts of the United States. Each detector consists of long, perpendicular tunnels with lasers aimed down them. When a gravitational wave passes through, it stretches one tunnel while compressing the other, producing minute shifts in the distances that can be measured with extraordinary precision. This groundbreaking event stemmed from the collision of two black holes over 1 billion light-years away. As the black holes spiraled toward each other, they released a staggering amount of energy, creating gravitational waves that traveled through the cosmos. When these waves reached Earth, they caused tiny fluctuations in the lengths of the tunnels at LIGO, confirming Einstein's century-old prediction that these waves exist. This discovery not only opened a new window to observe the universe, but also affirmed our understanding of fundamental physics, allowing us to explore cosmic phenomena that were previously hidden from view. The universe is a dynamic place, constantly changing as massive cosmic objects dance and interact with one another. When two massive objects, such as black holes or neutron stars, orbit each other, they create gravitational waves, ripples in the fabric of space and time. These waves are the echoes of some of the most violent and energetic events in the cosmos. As these objects draw closer together, their gravitational fields interact, causing them to accelerate. This acceleration disturbs the surrounding space, producing waves that propagate outward at the speed of light, similar to how a pebble creates ripples when tossed into a pond. The merging process itself is incredibly energetic, releasing a vast amount of energy as gravitational waves in a short burst, particularly during the final moments before the merger. Imagine two spiraling whirlpools merging into one. As they collide, they create powerful currents. In a cosmic sense, when two black holes or neutron stars finally merge, the gravitational waves emitted are the universe's way of conveying the tension and release of such a momentous event. These waves carry signatures of the objects involved, their masses, spins, and the dynamics of their merger, allowing scientists to listen to the universe in a way that is akin to tuning into a cosmic symphony. By studying these gravitational waves, researchers can uncover the secrets of the universe, gaining insights into the lives of massive objects and the intricate workings of gravity itself. Each merger tells a unique story, and as we continue to detect and analyze these waves, we draw closer to a deeper understanding of the cosmos. Gravitational waves have opened up a new frontier in our understanding of the universe, revealing the dynamic and ever-changing fabric of space-time. Imagine space-time as a vast, flexible sheet, and when massive celestial bodies like black holes or neutron stars move, they create ripples across this sheet, similar to throwing a stone in a pond. These ripples travel outward from their source at the speed of light, carrying crucial information about their origins. The detection of these gravitational waves has provided direct evidence that space-time is not a static backdrop, but rather a lively arena where events unfold dramatically. When two black holes collide, the resulting waves carry information about the objects involved, such as their masses and the energy released during the collision. This allows scientists to observe phenomena that are invisible to traditional telescopes, unveiling a new layer of cosmic events that were previously beyond our reach. Additionally, the study of gravitational waves is reshaping our understanding of the universe's evolution. These observations have confirmed theoretical predictions made by Einstein, demonstrating how extreme gravitational interactions influence the surrounding space-time. They have helped illustrate how dense regions of matter distort space-time, leading to profound consequences such as the bending of light or the slowing of time in intense gravitational fields. Through the lens of gravitational waves, we see space-time as a dynamic entity, constantly shaped by cosmic processes. This newfound perspective not only enriches our comprehension of the universe, but also opens up tantalizing possibilities for future research, as each wave detected provides a snapshot of the dramatic events occurring in the cosmos, bringing us closer to unraveling the mysteries of our universe. The study of gravitational waves marks a groundbreaking advancement in our understanding of the universe, introducing a new way of observing cosmic events. Gravitational waves are ripples in space-time created by massive accelerating objects, such as colliding black holes or neutron stars. Think of them as the echoes of powerful cataclysmic events reverberating across the cosmos. Unlike light or other forms of electromagnetic radiation that can be blocked or absorbed by intervening matter, gravitational waves travel freely through the universe. This means they carry information from the very origins of their sources, providing insights that were previously inaccessible. For instance, observing these waves helps scientists gather data about phenomena that are invisible to traditional telescopes, allowing us to understand events occurring billions of light years away. By capturing and analyzing these waves, researchers can uncover the properties of the objects that created them, how massive they are, how quickly they were moving, and even the nature of the extreme conditions under which they exist. This opens the door to studying the universe in a fundamentally different way, offering clues about the most energetic processes occurring throughout cosmic history. Additionally, the detection of gravitational waves has ushered in a new era of multi-messenger astronomy. This means that for the first time, scientists can simultaneously study signals from gravitational waves and traditional light waves. Observing the same cosmic phenomenon through different lenses enhances our understanding of stellar evolution and the fundamental forces of nature. Ultimately, gravitational waves not only deepen our knowledge of specific cosmic events, but also challenge our understanding of fundamental physics. As we refine our ability to detect these elusive signals, we pave new pathways to explore the origins of the universe itself, the fabric of space-time, and the mysteries that lie beyond our current comprehension. Gravitational wave astronomy opens the door to a range of exciting discoveries that could fundamentally change our understanding of the universe. By detecting the ripples in space-time caused by devastating cosmic events, such as colliding black holes or neutron stars, scientists can gain insights into some of the universe's most enigmatic phenomena. One of the most promising areas of exploration is the study of black hole mergers. As we gather more data, we might uncover the distribution of black holes throughout the universe, providing clues about their formation and evolution. These collisions could reveal details about the extreme conditions in their vicinity, enhancing our knowledge of gravity itself and testing the limits of Einstein's theories. Another significant potential lies in observing neutron star mergers. When these dense stellar remnants collide, they produce not only gravitational waves but also electromagnetic signals like gamma-ray bursts. By studying these events in both gravitational and light waves, scientists can learn about nuclear synthesis, the process that creates heavy elements, such as gold and platinum, in the universe. This collaboration could answer long-standing questions about where these elements originate. Future discoveries may also involve the detection of phenomena from the early universe. Some theories suggest gravitational waves could provide a glimpse into conditions that existed just minutes after the Big Bang. By tracing these primordial waves, researchers hope to gather evidence about the inflationary period, an expansion phase that dramatically shaped the universe. As technology advances in the field of gravitational wave detectors, we may also explore more exotic scenarios, such as the presence of new types of compact objects that challenge our current understanding of physics. This could include hidden black holes or even new theoretical entities that lie outside the well-established models. Moreover, imagine utilizing gravitational waves to study the dynamics of massive galaxies and their interactions. By observing waves from supermassive black holes located at galactic centers, we could unlock secrets about galaxy formation and behavior across cosmic time. Through gravitational wave astronomy, the future holds immense potential to broaden our understanding of the universe's puzzling workings while simultaneously placing fundamental physics under the microscope. As more discoveries accumulate, we stand on the brink of uncovering truths that could redefine the very fabric of reality itself. Rogue planets are fascinating celestial objects that travel through space without being tethered to any star. Unlike traditional exoplanets, which are planets that orbit a star, rogue planets roam freely in the galaxy. You can think of them as cosmic nomads, untethered and journeying through the vastness of space, having either formed in isolation or been ejected from their original star systems. Traditional exoplanets rely on their parent stars for light and warmth, making them part of a solar system's intricate dance. They follow specific orbits, influenced by the gravitational pull of their star. In contrast, rogue planets lack this relationship. They do not exhibit a predictable orbit around a star and can be found drifting in the dark, unseen by the light that typically illuminates distant worlds. The origins of rogue planets are varied. Some may have formed in the cold outskirts of a star system, where gravitational forces influence their ejection. Others could be remnants from collisions or disruptions in their original systems, flung away due to gravitational interactions. As they wander through space, rogue planets might still possess similar qualities to their star-bound cousins, such as atmospheres, geological features, and even the potential for life, though the conditions would be drastically different due to the absence of sunlight. Studying rogue planets presents unique challenges for astronomers. Detecting them requires specialized techniques, often focusing on subtle gravitational effects or the faint glimmer of heat they might emit, rather than the reflection of light from a star. These unruly wanderers expand our understanding of planetary formation and evolution, revealing the complexities of the universe's rich tapestry, where planets can exist in various states, some firmly anchored to their suns, and others endlessly drifting through the cosmic void. Scientists propose that rogue planets, those wandering worlds not tethered to any star, may originate from star systems in a couple of fascinating ways. One prevalent theory suggests that these planets form in a similar manner to traditional planets, forming in a protoplanetary disk around a young star. However, interactions with other celestial bodies can dramatically alter their fate. For instance, if two planets in close proximity gravitationally interact, one could be nudged away with enough force to escape the gravitational pull of its star. Another avenue for rogue planet formation is related to the dynamic environments of crowded star clusters. In these dense gatherings, gravitational encounters are frequent. A planet might get flung out during a close encounter with a larger body or another planet, effectively booted from its home system into the vastness of space. Additionally, scientists theorize that rogue planets can also form independently in cold regions of space, like dark interstellar clouds. In these environments, gas and dust can coalesce to create a planet directly without ever being part of a star system. These ejected planets now roam freely through galaxies, not bound to any star, creating a hidden population that challenges everything we know about planetary formation and survival. As they drift through the cosmos, scientists continue to explore the complexities surrounding their creation and existence, enriching our understanding of the universe's diverse structures. Rogue planets, those celestial bodies that wander through the cosmos without a parent star, present a fascinating scenario for the possibility of life. Unlike planets bound to a solar system, rogue planets drift in darkness, far from the warmth of their suns. At first glance, this solitary existence might seem inhospitable, but the potential for life can still be considered under certain conditions. One crucial aspect to explore is the heat within these planets. Many rogue planets may retain internal heat, generated from the energy released during their formation. This geothermal energy can create subsurface oceans or pockets of warm liquid, much like what scientists suspect exists beneath the icy crusts of some moons in our solar system. If these conditions are right, they could potentially support microbial life or other forms of simple organisms, similar to those found in extreme environments on Earth, such as deep-sea hydrothermal vents. Furthermore, the notion of life is not solely dependent on sunlight. Some life forms on Earth have adapted to thrive in complete darkness, utilizing chemosynthesis, deriving energy from chemical reactions instead of sunlight. In theory, if a rogue planet has the right chemical ingredients, it might foster similar life, utilizing the planet's own minerals to sustain biological processes. Additionally, there is the role of atmospheric conditions. A rogue planet with a thick atmosphere could retain heat and sustain pressure that might allow for liquid water to exist on its surface. The presence of water is often cited as a key ingredient for life, which opens a wider window of opportunity for different forms of existence. While rogue planets face numerous challenges due to their solitary nature and lack of sunlight, the potential for life isn't entirely ruled out. With internal heating, chemical energy sources, and favorable atmospheric conditions, these mysterious worlds could still nurture the seeds of life, albeit in forms we may not immediately recognize. This illustrates the remarkable resilience of life and its ability to adapt, even in the most unexpected of places within the universe. Detecting rogue planets, celestial bodies that wander through space without being tethered to a star, poses a unique challenge since they do not reflect the light of a nearby star like other planets do. However, astronomers have developed innovative methods to identify and study these elusive objects. One primary technique involves observing the gravitational influence of rogue planets on nearby objects. When a rogue planet passes close to another celestial body, it can alter that body's trajectory slightly due to the planet's gravitational pull. By monitoring these movements, astronomers can infer the presence of the planet. Another method relies on the phenomenon known as gravitational microlensing. When a rogue planet comes in line with a more distant background star, the planet's gravitational field can bend and magnify the star's light. This effect creates a temporary brightening of the star as seen from Earth, allowing astronomers to detect something that is otherwise invisible. By carefully analyzing the light curves of these events, researchers can gather crucial information about the rogue planet's mass and distance. In addition to gravitational effects, astronomers have begun employing infrared detectors. Rogue planets can emit heat, especially if they are relatively young and still cooling from their formation. These detectors can capture infrared wavelengths that the human eye cannot see, revealing the planet's presence through its own thermal radiation. Through these techniques, astronomers are gradually unveiling the mysterious lives of rogue planets, constructing a more complete picture of the diverse population of worlds that exist beyond the reaches of stars. This expanding knowledge not only stimulates our curiosity about these isolated planets, but also deepens our understanding of planet formation and the dynamics of our universe. Rogue planets, those wanderers drifting through the cosmos without a parent star, challenge our understanding of planetary systems in profound ways. These celestial bodies highlight that the universe is not just about stable orbits around stars. Instead, it reveals a dynamic and often chaotic environment where worlds can be ejected from their original systems. Imagine a planet, once part of a vibrant solar system, dislodged by gravitational interactions, now sailing alone through the vast expanse of space. This phenomenon prompts us to reconsider the conditions that can lead to the formation of planetary systems. Traditionally, we associate planets with stable, star-bound orbits. However, the existence of rogue planets hints at alternative scenarios where planets might form in isolation, perhaps around gas clouds, only to later be expelled from their birthplaces. This encourages scientists to explore the possibility of planets existing in solitude, completely independent of stars, possibly hosting unique environments and forms of life. Moreover, the presence of rogue planets can reshape hypotheses about planetary formation and evolution. When considering the mechanics of star formation and how planets develop, understanding how these solitary wanderers came to be offers valuable insight into the gravitational dances that form systems. It raises questions about how often these rogue planets can collide or interact with other celestial bodies, potentially creating new systems or influencing existing ones. Rogue planets also serve as a reminder of the mysteries that still await discovery in our universe. The possibility of their existence opens new avenues of research into how they interact with the cosmic environment, such as the ways they might contribute to gravitational interactions or elicit the migration of other celestial bodies. As we refine our tools and techniques for observing these elusive objects, our view of the universe becomes richer, emphasizing that planetary systems are not static, but instead are filled with potential for complexity and change. Cosmic voids are vast, empty regions of space that exist between the filaments and walls of galaxies, creating a fascinating structure within the universe. Imagine the universe as a giant web, where the strands are made up of galaxies clustered together, forming intricate shapes resembling bubbles in a frothy drink, while the spaces between these strands are the voids, enormous expanses largely devoid of matter. These voids can stretch billions of light-years across, a scale that is almost unimaginable. While they contain a much lower density of galaxies and dark matter, they are not completely empty. Occasionally, they hold a few isolated galaxies or clusters that manage to flourish despite the surrounding emptiness. Structurally, cosmic voids contribute significantly to the universe's overall arrangement. They are essential for understanding how galaxies have formed and evolved over cosmic time. By studying these voids, scientists gain insight into the gravitational forces at play in the universe and how matter is distributed on a grand scale. Furthermore, voids play a dynamic role in the universe's expansion. As the universe continues to grow, these empty regions expand as well, influencing nearby structures and contributing to the evolution of galaxies. The presence of cosmic voids helps create a balanced distribution of matter, offering a clearer picture of cosmic history and the forces that have shaped the universe since its inception. Voids are not just empty spaces, they are integral components that reveal the underlying fabric of the cosmos and its intricate design. Cosmic voids are vast, empty regions of space that can challenge our traditional views of how galaxies form and cluster. These areas are surprisingly large and relatively devoid of matter, contrasting sharply with the bustling clusters of galaxies that fill the denser parts of the universe. Imagine a sponge filled with water, where the water represents galaxies and the air pockets correspond to voids. The interesting aspect of these voids is that they play a crucial role in shaping the universe's structure. The existence of cosmic voids suggests that not all regions of the universe have gone through the same processes of growth and collapse that create galaxies. Traditional models of galaxy formation typically emphasize gravitational attraction, where gravity draws matter together to form stars and galaxies. However, in these enormous voids, the low density of matter means that fewer galaxies can form, and the ones that do become more isolated. This raises compelling questions about how galaxies evolve in environments that are not clustered together. Furthermore, cosmic voids influence the behavior of nearby galaxies as well. Their presence can change the flow of matter and radiation in the universe. For example, galaxies on the edges of these voids can experience different gravitational effects compared to those within dense clusters. This difference can lead to peculiar motions and variations in galaxy composition, challenging our understanding of how environments impact galaxy evolution. In recent studies, scientists have also found that voids might contain dark energy, which is believed to drive the universe's accelerated expansion. This potential connection adds another layer of complexity to our understanding of cosmic structures. As researchers delve deeper into the nature of these voids, we may uncover new insights into the underlying forces that shape our universe, revealing that even the emptiest regions are dynamic players in the grand tapestry of cosmic evolution. Astronomers employ a variety of sophisticated techniques to study cosmic voids, the vast empty regions of space that appear to have far fewer galaxies than other areas. To begin mapping these voids, scientists utilize large surveys of the night sky, systematically collecting data on the distribution and positions of galaxies. A prominent method includes utilizing telescope arrays that scan extensive areas, capturing detailed glimpses of galaxy clusters and their surrounding environments. One crucial technique is redshift surveys, where astronomers measure how light from distant galaxies shifts toward the red end of the spectrum. This shift indicates how fast these galaxies are moving away from us, which helps determine their distance. By mapping the three-dimensional distribution of galaxies based on their redshifts, scientists can visualize how these cosmic voids fit into the grand structure of the universe. Another method involves analyzing the cosmic microwave background radiation, the afterglow from the Big Bang. By studying fluctuations in this radiation, astronomers can infer the underlying distribution of mass throughout the universe, including the presence of voids. This ancient light provides a snapshot of the universe's early state and helps determine how matter, both visible and dark, has evolved over billions of years. Moreover, astronomers leverage computer simulations to model the large-scale structure of the universe. These simulations consider factors like dark matter and gravitational influences that affect how galaxies and voids form and develop over time. By comparing real observational data to these simulations, researchers can refine their understanding of cosmic voids, gaining insights into their origins and the role they play in cosmic evolution. Finally, the use of gravitational lensing, where light from distant objects is bent around massive structures, allows astronomers to map the distribution of dark matter in and around voids. This additional layer of data helps paint a more complete picture of the voids and their surroundings, revealing more about the hidden forces shaping our universe. Through the combination of these powerful methods, astronomers steadily unravel the mysteries of these enigmatic cosmic voids, enhancing our understanding of the universe's vast and intricate web. Cosmic voids are some of the largest structures in the universe, vast expanses where very few galaxies can be found. These regions are remarkably different in their dynamics compared to the denser parts of the universe, such as galaxy clusters. In dense regions, gravity plays a major role, pulling galaxies together and causing interactions that lead to the formation of clusters. There, galaxies are packed closely together, resulting in a rich environment filled with gravitational forces, influencing the movement and behavior of these celestial bodies. In contrast, within a cosmic void, the gravitational pull between galaxies is much weaker. This sparse environment means that galaxies are isolated, allowing them to travel through the void with less interference from neighboring galaxies. As a result, the dynamics in cosmic voids are more influenced by the expansion of the universe itself. The expansion creates a scenario where galaxies within voids can drift apart from each other, moving along paths determined largely by the overall cosmic expansion rather than interactions with other galaxies. Moreover, the lack of material in these voids also affects the surrounding dark matter. Since dark matter is thought to play a critical role in the formation of structure in the universe, its reduced density in voids means that cosmic events affecting the motion and clustering of galaxies are minimal. Instead of being shaped by the gravitational influences of their neighbors, galaxies within voids are often subject to the slow, steady influence of the universe's expansion, illustrating a stark contrast to the tumultuous interactions found in denser areas. Thus, dynamics in cosmic voids reveal a more tranquil cosmic environment, characterized by solitude and the relentless movement dictated by the universe's expansion, while the energetic clustered regions highlight the active interplay of gravitational forces shaping the cosmos. Cosmic voids are vast, underdense regions in the universe, where fewer galaxies are found compared to average regions. Think of a sponge, with its many holes and dense areas. Those holes represent cosmic voids, while the dense areas are rich in galaxies and clusters. When scientists study the universe, they often build models assuming it is homogeneous, meaning it is uniform on a large scale, and isotropic, indicating it looks the same in every direction. However, the presence of these voids introduces a significant nuance to our understanding. If you gaze into the cosmos, what you observe is the light from the galaxies. In areas with substantial voids, there is simply less light available due to the scarcity of galaxies and clusters. This can create an illusion of a less structured universe, leading to the potential misinterpretation of isotropy and homogeneity. Furthermore, cosmic voids impact the gravitational lensing effect, where massive structures bend the light from more distant objects. In voids, where mass is less concentrated, the bending is minimal, further complicating our observations. The relatively empty nature of these voids can influence the distribution of matter and energy, affecting the broader characteristics of the universe. As we piece together the cosmic puzzle, the existence of these voids challenges our assumptions. Recognizing them as significant players in the large-scale structure of the universe helps scientists refine their models, leading to a more accurate portrayal of cosmic evolution and the large-scale structure that governs our universe. Thus, cosmic voids do more than just sit quietly in space. They encourage us to consider the intricacies of how the universe is organized and how we perceive it. Quasars, or quasi-stellar objects, are some of the most luminous and energetic phenomena in the universe. They appear as bright points of light, similar to stars, but they are actually the centers of galaxies that house supermassive black holes. These black holes possess masses millions to billions of times greater than that of our Sun. The intense energy output of quasars originates from the material surrounding these supermassive black holes, which is often composed of gas and dust. As this material spirals closer to the black hole, a process known as accretion, it heats up dramatically due to gravitational and frictional forces. This heating causes the gas to emit enormous amounts of energy, primarily in the form of light across a wide spectrum, from radio waves to X-rays. What makes quasars particularly fascinating is their ability to outshine entire galaxies. The energy produced when matter is consumed by the black hole can be trillions of times greater than that of our Sun. In fact, a quasar can emit energy equivalent to thousands of galaxies combined. The sheer scale of this energy release is indicative of the efficiency of converting mass into energy, driven by the powerful gravitational field of the black hole. Quasars also serve as important tools for astronomers. Their extreme brightness allows scientists to observe them from vast distances, providing insights into the early universe and the formation of galaxies. By studying quasars, we gain valuable information about cosmic evolution and the fundamental forces that shape our universe. Quasars, or quasi-stellar objects, serve as guideposts to the early universe, illuminating the conditions that existed billions of years ago. Imagine looking at a distant lighthouse through a foggy night. The light reaching you is not just a beacon, but a window into the past. Quasars are incredibly luminous centers of distant galaxies powered by supermassive black holes. When matter spirals into these black holes, it heats up to extreme temperatures, emitting vast amounts of energy that can outshine entire galaxies. By studying quasars, astronomers can glimpse the universe when it was still in its youth, as they formed during a period known as the cosmic dawn. These objects are often seen as they were just a few 100 million years after the Big Bang, providing valuable insights into the makeup and behavior of the universe at that time. The light from quasars allows scientists to analyze how galaxies formed and evolved, giving clues about the processes that led to star formation and the materials that constitute galaxies. Another fascinating aspect of quasars is their ability to reveal the cosmic web, the large-scale structure of the universe. Their light can interact with gas and dust in space, which allows researchers to study the state of intergalactic matter. This is akin to passing a flashlight through fog. You not only see the light, but also learn about the density and distribution of particles in the air. This helps astrophysicists piece together a timeline of galaxy formation, mapping how they clump together in the vastness of space. Furthermore, the redshift of quasar light indicates how fast the universe is expanding. This expansion provides context for understanding both the rate of new star creation in ancient galaxies and the influence of dark energy today. Quasars are not just curiosities of the cosmos. They are pivotal in constructing the narrative of galactic evolution and the universe's early epochs, helping us think about how we got to the universe as we know it today. A quasar is a remarkable cosmic phenomenon, often considered one of the most luminous objects in the universe. At their core, quasars are powered by supermassive black holes at the centers of distant galaxies, actively consuming vast amounts of surrounding gas and dust. This intense feeding process generates enormous energy, emitting light that can outshine entire galaxies. Over time, however, the materials available for a quasar to consume can dwindle. This depletion can occur as the black hole exhausts its immediate surroundings, leading to a significant drop in energy output. Without a steady influx of fuel, the quasar begins to dim. As it becomes less active, it transitions into a dormant state. The timeline of a quasar's active phase varies widely, with many lasting for millions to billions of years, while others may exhibit brief periods of luminosity before fading. This variability suggests that the life cycle of a quasar can be influenced by several factors, including the rate at which the black hole consumes material and the availability of that material in its environment. Once dormant, these magnificent entities can remain in this state for an exceedingly long time, potentially across billions of years, until conditions once again allow for renewed activity. During this dormancy, the supermassive black hole quietly exists at the galaxy's heart, waiting for the cosmos to align in such a way that reignites its brilliant light. Quasars are among the most luminous objects in the universe, and they play a significant role in our understanding of cosmic structure and development. When we look at the distribution of quasars, we find that they are primarily situated in regions that host massive galaxies. These galaxies are actively growing, feeding their supermassive black holes, which in turn release energy in the form of light across vast distances. Observations reveal that quasars are more frequently located at great distances from Earth, suggesting that many of them are from earlier epochs of the universe. This distribution illustrates a fascinating trend. As we gaze deeper into space, we are also looking back in time. The light from these distant quasars has taken billions of years to reach us, allowing scientists to study the conditions of the universe when it was much younger and more dynamic. The clustering of quasars indicates areas where galaxy formation and evolution have been particularly active. By studying their locations, researchers can glean insights into how galaxies and large-scale structures evolved. The patterns in which quasars are distributed can inform us about the universe's history, highlighting the influence of gravity in shaping cosmic structures over time. The presence of a dense concentration of quasars may signal a rich environment of galaxies, providing clues to the processes that governed the early universe's formation. Quasars are among the most luminous objects in the universe, shining with an intensity that can outshine entire galaxies. Yet they remain shrouded in mystery, particularly regarding the mechanisms that fuel their incredible energy output. At their core, quasars are powered by supermassive black holes, which can contain millions to billions of times the mass of our Sun. As matter spirals into these black holes, it forms an accretion disk, a rotating disk of gas and dust spiraling inward. The primary source of a quasar's luminosity stems from this accretion process. When material in the disk gets incredibly hot due to friction and gravitational forces, it emits vast amounts of electromagnetic radiation, often outshining everything around it. However, the exact processes that enable this transformation into such powerful radiation are not fully understood. One mystery lies in the nature of the accretion disk itself. Scientists are still investigating how varying temperatures and chemical compositions influence its behavior and the rate at which material feeds into the black hole. Additionally, the phenomena of jets, powerful streams of particles shot out at nearly the speed of light from the regions near a quasar, add another layer of complexity. These jets are thought to be formed by magnetic fields interacting with the accretion disk, but details about their formation and the exact physics at play remain elusive. Furthermore, the evolution of quasars over cosmic time raises additional questions. We see them mostly in the earlier universe, where they appear to thrive. The relation between the growth of supermassive black holes and the galaxies they inhabit is still being explored. How do these black holes and their host galaxies influence each other's growth, and what roles do mergers and interactions play? As we probe deeper into the universe's history using advanced telescopes and observatories, each new discovery about quasars opens more questions, beckoning an exploration into the unknown. The quest to fully understand these enigmatic beacons of light is not just about unraveling their secrets, but also gaining insight into the fundamental workings of the cosmos. Fast radio bursts, commonly known as FRBs, are powerful and fleeting bursts of radio waves originating from beyond our galaxy. They last only a fraction of a second, yet can emit energy equivalent to what the Sun produces over several days. This immense energy and brevity make them particularly intriguing in the field of astrophysics. What sets FRBs apart from other cosmic signals is their rapid occurrence and mysterious origins. While many astronomical phenomena such as supernovae or pulsars typically have prolonged or cyclical emissions, FRBs stand out because of their singular, intense nature. The exact source of these bursts is still a subject of active research, with theories ranging from magnetars, highly magnetized neutron stars, to more exotic possibilities like interactions with black holes or even extraterrestrial technology. Furthermore, FRBs are distinguished by their distinct patterns of radio frequency emissions. Some of them seem to repeat, offering a tantalizing glimpse into their behavior, while others appear only once, adding a layer of complexity to their study. This uniqueness fuels ongoing investigations as scientists endeavor to understand not only their origins, but also how they fit into the larger tapestry of the universe. As we delve deeper into the mysteries of FRBs, we uncover clues that may lead us toward new insights about cosmic events and the nature of reality itself. Fast radio bursts, or FRBs, are brief, intense flashes of radio energy from distant galaxies that have captivated astronomers since their first discovery. Initially shrouded in mystery, recent findings have broadened our comprehension of these enigmatic events. Now, a variety of potential sources have been proposed, moving beyond the early assumption that they may be linked to highly violent cosmic phenomena. One of the key discoveries is the connection between some FRBs and magnetars. These are highly magnetic, rotating neutron stars that can release bursts of energy. Observations have shown that a specific type of FRB, known for repeating, aligns with the behaviors of magnetars, leading scientists to consider them as significant contributors to these signals. Their extraordinary magnetic fields could be responsible for the intense energy release observed. Furthermore, studies have indicated that certain FRBs are originating from environments with high-density interstellar matter. This suggests that the conditions surrounding the source can influence how these bursts are produced. By analyzing the scattering of the signals, researchers found clues about the material between us and the FRB, hinting at the presence of dense clouds that might interact with the radio waves, leading to their unique signatures. New telescope technologies and observational projects have also played a crucial role in tracking these bursts with unprecedented detail. Through advancements in radio astronomy, the ability to pinpoint their origins helps researchers identify different celestial environments and contexts, which is reshaping our perspective on where and how these bursts occur. In sum, the expansion of our understanding of FRBs has revealed a diverse array of potential sources, from magnetars to interactions with interstellar material, and has sparked a significant interest in the cosmic environments that give rise to these captivating radio flashes. Each finding adds a new piece to the puzzle, allowing us to better appreciate the complexity and dynamics of our universe. Fast radio bursts, or FRBs, have revolutionized our understanding of the universe, and advancements in technology have played a crucial role in enhancing our ability to detect and study these mysterious cosmic events. One significant improvement has been in the sensitivity of radio telescopes. Modern telescopes can capture fainter signals, enabling them to observe FRBs that might have gone unnoticed with older instruments. These telescopes often use large arrays of antennas, allowing them to gather more data over a wider area of the sky simultaneously. Another key advancement is in the processing power of computers. Today, complex algorithms can analyze the massive influx of data generated by these telescopes in real time. This swift processing capability means that potential FRB signals can be detected almost instantaneously, leading to quicker observations and further studies. Machine learning techniques are now employed to differentiate between actual cosmic events and noise, refining our understanding of these enigmatic bursts. The development of more precise timing techniques also enhances our capacity to study FRBs. By synchronizing multiple telescopes around the globe, scientists can pinpoint the location of FRBs with unprecedented accuracy. This precise geolocation allows researchers to trace the bursts back to their host galaxies, shedding light on their origins and the environments in which they occur. Furthermore, advancements in the design of observational programs have enabled astronomers to monitor the sky more efficiently. Continuous monitoring and dedicated surveys have increased the chances of detecting FRBs, which are fleeting by nature. These sophisticated observational strategies have transformed the once sporadic discoveries of FRBs into a systematic scientific endeavor. Lastly, the integration of multi-wavelength observations, combining radio, optical, and even gamma-ray data, has provided a richer context for understanding FRBs. By analyzing these bursts across different parts of the electromagnetic spectrum, researchers can gather invaluable insights into the physical processes that create them. Together, these technological advancements form a robust framework that propels future investigations into FRBs and their role in the cosmic landscape. Fast radio bursts, or FRBs, are among the universe's most enigmatic phenomena, first detected in 2007. They are brief, intense bursts of radio waves that last only milliseconds, but produce as much energy in that short time as the sun emits in a year. The origins and nature of these bursts have stirred curiosity and prompted various theories. One leading explanation is that FRBs may originate from extreme astrophysical events. For instance, the merging of neutron stars, a process resulting in incredible gravitational forces, could generate the necessary conditions for these bursts. Another candidate is magnetars, which are a type of neutron star with extraordinarily strong magnetic fields. Certain activities on or near their surfaces might result in bursts of radio waves akin to flares. Some researchers have proposed that FRBs could be related to more exotic phenomena, such as the collapse of massive stars or even extraterrestrial technologies. although the latter remains far more speculative and controversial. Researchers continue to investigate the potential links between FRBs and the environments in which they occur, suggesting that different types of bursts may stem from various cosmic sources. The localization of some FRBs to specific galaxies has opened new doors for understanding their nature. By analyzing the host galaxies, scientists can glean insights about the environments surrounding these events. It appears that the magnetic fields and the density of the material in these galaxies may influence the characteristics of the radio bursts. Ultimately, while we do not yet have a definitive answer, the ongoing observation and study of FRBs are likely to reveal more about their origins. Each new discovery may piece together the larger puzzle of how such spectacular events fit within the cosmic tapestry. As technology evolves and telescopes become more powerful, we inch closer to unraveling the mysteries of these celestial phenomena. Fast radio bursts, or FRBs, are brief but intense flashes of radio waves originating from distant galaxies. These mysterious phenomena have captivated astronomers and scientists because their study offers a unique window into intergalactic space. Each FRB carries a wealth of information about the environment it travels through before reaching us. As these bursts journey across vast cosmic distances, they interact with the matter and energy in their path. This interaction can provide clues about the density and distribution of gas, dust, and other elements scattered throughout intergalactic space. When we analyze the signals from FRBs, inconsistencies in their frequency reveal changes caused by the intervening medium, like how sound can warp as it moves through different atmospheres. Such data can help map the distribution of matter in regions of space that are otherwise difficult to observe. Moreover, FRBs may hold secrets about cosmic events leading to their bursts, such as the collisions of neutron stars or the activities of magnetars, types of neutron stars with extremely strong magnetic fields. Understanding these triggers helps illuminate the life cycles of stars and the energetic processes driving galactic evolution. Another vital aspect is that FRBs can act as probes for cosmic expansion. As these radio waves traverse the universe, their properties may change due to the expansion of space itself. By studying fluctuations in their signals across different distances, scientists can learn more about the ultimate fate of the universe and the dynamics of dark energy. Fast radio bursts are not just fleeting signals, they are messengers from the furthest reaches of the universe, offering profound insights about the nature of intergalactic space and challenging our understanding of the cosmos. The more we study them, the clearer the picture of our universe's structure and history becomes, one burst at a time. Gamma-ray bursts are fascinating and incredibly powerful phenomena, marking some of the most energetic events in the universe. These bursts can occur when massive stars reach the end of their life cycles. As they exhaust their nuclear fuel, they may collapse under their own gravity, leading to the formation of black holes or neutron stars. This collapse can cause a rapid outflow of energy, releasing beams of gamma rays that travel outwards into space. Another route to gamma-ray bursts involves the collision of neutron stars. When two of these dense and compact objects spiral towards each other and ultimately collide, they produce massive amounts of energy. The energy released during these encounters is so intense that it can brightly outshine entire galaxies for a brief moment. What makes these bursts truly remarkable is their intensity. A single gamma-ray burst can emit more energy in just a few moments than the sun will release over its entire lifespan. This extraordinary output is largely due to the extreme conditions present during the events, like the intense gravitational forces and the rapid acceleration of particles. In short, gamma-ray bursts not only capture our attention because of their sheer power, but also offer insights into the fundamental processes occurring during some of the universe's most violent moments. Gamma-ray bursts, the most energetic explosions observed in the universe, have significantly advanced our understanding of stellar life cycles and the dramatic events that occur at their end. These bursts are believed to originate from massive stars that explode after exhausting their nuclear fuel. As these stars reach the final stages of their life cycle, they undergo a core collapse, resulting in either a supernova or a more complicated process that leads to a gamma-ray burst. By studying these bursts, scientists have gathered insights into the birth and death of stars. The explosion of a massive star reveals information about the processes that govern stellar evolution. Observations of gamma-ray bursts help identify the types of stars that end their lives this way, allowing for a clearer understanding of which conditions lead to these powerful events. For instance, we have learned that certain massive stars, specifically those that can form black holes, are the primary candidates for generating these bursts. Furthermore, the afterglow of gamma-ray bursts, visible across various wavelengths, allows astronomers to examine the surrounding environment and conditions at the moment of explosion. This provides clues about the stellar material that existed before the star's death and the effects of such explosions on nearby stellar systems, enriching our understanding of how stars interact with their environments. Moreover, researching gamma-ray bursts has revealed their role in metal enrichment of the universe. When these massive stars explode, they distribute heavy elements formed in their cores into the cosmic environment, impacting the formation of new stars and planets. This process plays a crucial role in the evolution of galaxies. The study of gamma-ray bursts serves as a powerful tool for unraveling the mysteries of stellar life cycles, shedding light on how stars form, evolve, and ultimately transform, influencing the very fabric of the universe. Each discovery brings us one step closer to understanding not just the life of individual stars, but the cosmic processes that shape the night sky we observe today. Gamma-ray bursts, some of the most energetic explosions in the universe, are closely linked to the dramatic final stages of massive stars and the cosmic aftermath of neutron-star collisions. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, a cataclysmic event marking the star's death. In certain situations, this explosion can trigger a gamma-ray burst. As the star collapses under its gravitational pull, it can create a highly energetic jet of particles that accelerates close to the speed of light, releasing incredible amounts of gamma radiation in a narrow beam. If Earth happens to be aligned with this beam, we observe a brief but intense flash of gamma rays. On the other hand, neutron star collisions generate another type of gamma-ray burst, known as short-duration bursts. Neutron stars are the remnants of supernovae and are incredibly dense, with two of them in close orbit. When these stars spiral into each other, they can collide in an explosion that releases a significant amount of energy. This catastrophic merger produces jets of gamma rays, accompanied by the creation of heavy elements, such as gold and platinum. The energy released during the collision and the subsequent formation of these jets can also lead to powerful bursts of gamma radiation. Both processes highlight the dynamic and interconnected nature of cosmic events, where the death of one star can give rise to immense energy emanating from another, illuminating our understanding of the life cycle of stars and the universe itself. Gamma-ray bursts, the most energetic explosions in the universe, capture both intrigue and caution. These bursts are thought to originate from extreme cosmic events, such as the collapse of massive stars or the collision of neutron stars. When they occur, they release immense amounts of energy in the form of gamma rays, which can outshine entire galaxies for brief moments. On one hand, these bursts pose a potential threat to life on Earth. If a gamma-ray burst were to occur close enough, the intense radiation could disrupt our atmosphere, harm our ozone layer, and ultimately affect biological processes crucial to life. Even though the odds of such an event happening in our cosmic neighborhood are quite low, the sheer scale of energy involved raises valid concerns about their impacts. Conversely, gamma-ray bursts serve as profound opportunities for scientific discovery. They present a unique window into the life cycles of stars and the physics of high-energy phenomena. When observed, these bursts provide valuable data that scientists can analyze to gain insights into the formation of black holes and the behavior of matter under extreme conditions. Watching how these massive explosions unfold allows researchers to test theories of fundamental physics and understand the universe's evolution on a grand scale. Thus, while gamma-ray bursts remind us of the potential dangers lurking in the cosmos, they also illuminate pathways to knowledge about the universe that we might otherwise never explore. They challenge our understanding and inspire curiosity, emphasizing the duality of risk and reward that characterizes much of space exploration. Gamma-ray bursts, the most energetic explosions in the universe, pose significant challenges for scientists who seek to understand their nature and predict their occurrences. One major hurdle is the sheer unpredictability and rarity of these events. A gamma-ray burst can happen in any corner of the universe at any time, and there's currently no reliable method to anticipate when or where they will occur. This inherently makes it difficult to observe them as they happen, as the brief flashes of gamma rays may only last from a few milliseconds to several minutes. Additionally, these bursts can be incredibly distant. The light from a gamma ray burst can take billions of years to reach us, meaning that when we observe one, we are seeing it as it was long ago. This distance not only complicates observational efforts, but also means that by the time a burst is detected, much of its energy has dispersed. The vast expanses of space also pose challenges in terms of the energy absorption and scattering of the gamma rays, which can weaken the signal and make it harder to analyze. Scientists also grapple with understanding the underlying mechanisms that generate these powerful bursts. While two primary types are known, short bursts linked to the collision of neutron stars and long bursts associated with massive star collapses, many details remain uncertain. The extreme conditions involved, such as the intense gravitational fields and high-energy processes, push the boundaries of our current physics theories, leaving many questions about how these phenomena function. Lastly, there is the technological aspect. Observing gamma-ray bursts requires sophisticated instruments capable of detecting high-energy radiation. While telescopes designed for this purpose have made significant advancements, they still face limitations in detecting the full range of bursts and interpreting the data accurately. Integrating observations from various wavelengths, such as X-rays and radio waves, adds another layer of complexity. As scientists continue to enhance detection methods and improve theoretical models, the study of gamma-ray bursts remains a dynamic field filled with both challenges and opportunities for groundbreaking discoveries. The cosmic microwave background radiation, often called CMB, is like a faint echo of the Big Bang, the event that launched our universe into existence billions of years ago. Imagine the universe beginning in a hot and dense state. As it expanded, it cooled, allowing energy to transform into matter. However, there remained a glow of energy permeating the universe, which eventually stretched and cooled further as space itself expanded. This leftover radiation now fills space and is detectable everywhere we look. It appears as a uniform and distant hum of microwaves, which is why we refer to it as the cosmic microwave background. Its significance lies in what it tells us about the early universe. By studying the variations in this radiation, scientists can glean information about the conditions that existed shortly after the Big Bang. The tiny fluctuations in temperature within the CMB provide a snapshot of the density of matter throughout the universe when it was just a fraction of its present age. These patterns are essential for understanding the universe's structure, including how galaxies formed and evolved over time. Moreover, the existence of CMB supports the theory of cosmic inflation, which posits a rapid expansion of the universe during its earliest moments. Essentially, the cosmic microwave background is a crucial relic from the past, offering a window into the origins and evolution of everything we see around us today. In our quest to understand the universe, various types of cosmic backgrounds provide essential clues about its history and structure. Neutrino backgrounds and gravitational wave backgrounds represent two distinct yet vital components of this cosmic puzzle. Neutrinos are elusive particles that are produced in vast quantities during cosmic events, such as supernova explosions or cosmic ray interactions. Because they interact very weakly with matter, neutrinos can travel almost unimpeded through the universe, carrying information from their sources across immense distances. By studying the cosmic neutrino background, scientists can gain insights into processes occurring in the early universe, including the formation of matter and the behavior of stellar objects. This background can act as a window into phenomena that would otherwise be hidden from view, revealing the energetic events that shaped our cosmos. On the other hand, gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe, such as colliding black holes or neutron stars. These waves travel at the speed of light and can stretch and compress space itself as they pass through it. The detection of gravitational waves has opened an entirely new field of astrophysics. By analyzing the gravitational wave background, scientists can explore the population and evolution of massive cosmic objects and the dynamics of extreme environments. This not only deepens our understanding of fundamental physics, but also provides a complementary way to observe the universe, filling in gaps left by traditional electromagnetic observations. Together, the study of neutrino and gravitational wave backgrounds enriches our comprehension of the universe's life cycle, from its explosive beginnings to the interactions of the most fundamental forces at work. These backgrounds serve as a vast archive of cosmic information, challenging our existing models and inspiring new ideas about the nature of reality itself. By integrating these insights with observations from other cosmic phenomena, we can weave a more complete narrative of the cosmos, illuminating its past while guiding our exploration of the future. The cosmic backgrounds, particularly the cosmic microwave background radiation, are remnants of the early universe, offering a fascinating glimpse into its infancy. Despite decades of extensive research, this primordial soup of energy still shrouds many mysteries. Scientists have mapped the tiny fluctuations in temperature across this background, which are indicators of the early density of matter. However, the precise mechanisms that led to the structures we observe today, like galaxies and clusters, remain an open question. Another enigmatic aspect involves dark energy, which is believed to drive the accelerated expansion of the universe. The cosmic backgrounds provide indirect clues about this elusive force, yet they do not explain its nature or origin. This creates a divide. While we can track how fast the universe is expanding, we still lack a clear understanding of what is causing this expansion to speed up. Moreover, cosmic backgrounds hint at potential interactions beyond our current physics. Some theories suggest there could be multiple universes, or that our universe might be part of a multiverse, but these ideas remain speculative and require more evidence. Lastly, there are the intriguing anomalies observed in the cosmic background data that challenge conventional models of the universe. These unusual features could either be signs of new physics or potential errors in our measurements. While we have learned a great deal, the cosmic backgrounds serve as both a record of the universe's past and a tantalizing invitation to unravel the mysteries that lay ahead. There's still so much to explore, pushing the boundaries of our knowledge and inviting a deeper inquiry into the nature of existence itself. Cosmic backgrounds are like ancient photographs, capturing the universe at different stages of its development. One of the primary cosmic backgrounds we study is the cosmic microwave background radiation, which is the afterglow of the Big Bang. This faint glow fills the entire universe and originated when the universe cooled enough for light to travel freely, roughly 300,000 years after its explosive birth. At that moment, the universe transitioned from an opaque fog into a transparent space, allowing this light to reach observers today. Through careful analysis of the cosmic microwave background, scientists can glean information about the conditions of the early universe, including its temperature, density, and the distribution of matter. Variations in this background radiation reveal tiny fluctuations, which are crucial because they indicate where galaxies would eventually form. Each of these fluctuations acts as a relic from a specific moment in time, providing insights into how the universe grew and evolved over billions of years. In addition to the cosmic microwave background, other cosmic backgrounds such as the gravitational wave background capture events like merging black holes and neutron stars. These events send ripples through space-time, creating a form of background noise that can be studied to understand the dynamics of the universe during its most energetic epochs. By piecing together these cosmic snapshots, astronomers construct a timeline of cosmic history, revealing how galaxies, stars, and planetary systems came into existence, and how cosmic forces shaped the universe as we know it today. Thus, these backgrounds are not just remnants of past events. They are vital clues that help us unravel the complex story of the cosmos, from its fiery beginnings to its current state. Future telescopes and missions are set to revolutionize our understanding of the cosmic backgrounds, which are the faint afterglows of significant events in the history of the universe. These backgrounds include the cosmic microwave background radiation, the remnants of the Big Bang, and the infrared light that tells the story of the first stars and galaxies. With advanced technology, these new missions will enhance our observational capabilities, allowing us to peer deeper into space and time than ever before. Imagine being able to look back in time to when the universe was still young, just a few 100,000 years old. Upcoming missions equipped with sensitive detectors will be able to capture incredibly faint signals from that early era, giving us clues about the conditions that prevailed at that time. This endeavor is not just about seeing what's out there, it's about understanding the fundamental processes that shaped the universe. Moreover, future telescopes will utilize a variety of wavelengths, from radio to optical to infrared. Each range provides unique insights. For example, infrared observations can reveal hidden galaxies obscured by cosmic dust, while radio frequencies can unveil the mysterious processes that affect the formation of cosmic structures. By piecing together these diverse observations, scientists will construct a more complete picture of the evolutionary history of our universe. Additionally, advancements in technology, such as adaptive optics and larger apertures, will help mitigate the distortion caused by Earth's atmosphere. This means sharper and more precise images, allowing astronomers to differentiate between small variations in the cosmic backgrounds that might tell us something significant, such as the physics of primordial fluctuations. As we embark on this new era of exploration, the synergy between these innovative telescopes and missions will not only deepen our knowledge of cosmic backgrounds, but could also lead to unexpected discoveries. We might uncover new phenomena or challenge existing theories, reshaping our comprehension of the cosmos and our place within it. Ultimately, these efforts will bring us closer to answering fundamental questions about the vitality of the universe, the formation of structures, and the possible existence of regions yet unknown to us. The search for a potential ninth planet beyond Neptune has captivated astronomers and scientists for years. One of the leading theories suggests that the outer regions of our solar system are home to a massive object, commonly referred to as Planet 9. The hypothesis centers around unusual gravitational effects observed in the orbits of distant celestial bodies, known as trans-Neptunian objects. These bodies, which have eccentric or unusual orbits, appear to cluster together in a way that can't be easily explained by the gravitational influence of the known planets alone. Researchers propose that a planet, significantly larger than Earth but smaller than Neptune, could be lurking in the shadows of the solar system. This hypothetical planet would have a highly elongated orbit, taking it far beyond the current known planets, causing it to spend much of its time in an area far from the Sun. Its presence could exert a gravitational pull on other objects in the Kuiper belt, aligning their orbits in a manner that aligns with these observed anomalies. Another theory ties into the idea of the solar system's formation. Early in the solar system's history, it suggested that other planets might have been flung out into interstellar space or even collided, potentially leaving behind a remnant. This could mean that Planet 9 is not just a massive object, but perhaps an object whose formation was uniquely shaped by the disruptive forces of the solar system's infancy. Searching for Planet 9 involves looking for gravitational influences in the distant reaches of space. Scientists utilize advanced telescopes to scan the dark expanse, hypothesizing where this unseen planet could be based on the gravitational effects they measure on other bodies. So far, no direct observation of this mysterious planet has been confirmed, but the quest continues, driven by the desire to confirm not just its existence, but to learn more about the structure and evolution of our solar system. Trans-Neptunian objects, or TNOs, reside in the cold, distant regions beyond Neptune. These objects often follow orbits that are highly eccentric or even inclined in strange ways compared to the typical orbits of planets. This unusual behavior raises intriguing questions about the formation and evolution of the solar system. Picture a vast expanse where some objects travel in elongated paths, while others appear to be on their own unique trajectories, creating an overview that looks more like a chaotic dance than the orderly movements we see with the major planets. The irregularity of these orbits suggests that there could be additional forces at play or undiscovered bodies influencing the paths of these distant objects. For instance, some scientists speculate about the existence of a large, unseen planet, often referred to as Planet 9, that might exert gravitational pull on these TNOs, skewing their orbits. Such a presence could provide insight into the dynamics of the outer solar system and the forces that shape its architecture. Moreover, the discovery of these unusual orbits prompts questions about the early history of the solar system. Was there a time when these objects were closer to the Sun, only to be scattered outward by the gravitational influences of forming planets? Each unique trajectory tells a story of cosmic interactions, likely involving collisions, gravitational assists, or even the remnants of the early solar system's gas and dust clouds. As researchers delve deeper into the patterns of these orbits, they uncover clues about the environment at the farthest edges of our solar system. This exploration not only broadens our understanding of these distant worlds, but also challenges our foundational theories about how our solar system formed and evolved, encouraging scientists to rethink what they know about planetary formation and celestial dynamics. The mystery of the outer reaches continues to unfold, one intriguing orbit at a time. The Kuiper Belt and the Oort cloud are two enigmatic regions of our solar system that present significant challenges for scientists. The Kuiper Belt lies just beyond the orbit of Neptune, filled with icy bodies and dwarf planets. Understanding this area requires not only advanced instruments, but also the ability to navigate vast distances in a region that is incredibly dark and cold. One of the major obstacles is the sheer expanse of space. Even our most powerful telescopes can only detect a fraction of its objects, making it difficult to map and study these distant worlds comprehensively. The Oort cloud, even more remote, is believed to encompass a massive sphere surrounding our solar system, filled with icy objects and potential comets. Its distance from the Sun makes it almost invisible to current observational technology. The objects there are faint and far away, leading to difficulties in detection. This means that scientists have to rely on indirect methods to infer its existence and composition, often using mathematical models and observations of comet trajectories to piece together its characteristics. Another challenge arises from the dynamic nature of these regions. Objects in the Kuiper Belt and Oort cloud don't remain static. They exist in a constant state of motion influenced by gravitational interactions. These interactions can alter their paths, complicating our understanding of their origins and evolution. Additionally, many of the celestial bodies may have formed in different parts of the solar system and could provide clues to the early solar system's history, but tracking their movements accurately is a daunting task. Moreover, missions designed to explore these regions require years of planning and execution. The probe must be equipped to withstand extreme conditions, including fierce radiation, low temperatures, and the immense distances involved that stretch travel times to many years. Thus, every mission carries significant risk, and the data returned can only offer a glimpse into these far-off realms. The exploration of both the Kuiper Belt and the Oort cloud is fraught with challenges ranging from technological limitations to the inherent difficulties of studying distant, dynamic regions in space. Each obstacle presents opportunities for innovation as scientists continue to push the boundaries of our understanding of these mysterious and vital areas of our solar system. Comets and asteroids, particularly those found in the outer regions of our solar system, are like time capsules from the past. They formed in the early solar system, remaining relatively unchanged over billions of years. Studying these celestial bodies offers a compelling glimpse into the conditions that existed when our solar system was still taking shape, around 4.5 billion years ago. When scientists analyze the composition of comets and asteroids, they uncover valuable information about the materials that were present during the solar system's formation. For instance, many comets harbor ice, dust, and organic compounds, remnants of the primordial clouds that birthed our Sun and its surrounding planets. Understanding the proportions of these components can help us piece together the story of how the planets developed and evolved over time. Furthermore, the orbits of these bodies provide insights into the dynamical processes that have shaped our solar system. As comets and asteroids travel through space, they sometimes interact with the gravitational fields of nearby planets. These encounters can alter their paths, revealing how celestial mechanics has influenced their movement and distribution. By tracing these trajectories backwards, researchers can infer the gravitational interactions that have occurred throughout history. Moreover, the impact history of our planet is closely linked to these objects. Over millions of years, asteroids and comets have made their way towards the inner solar system, occasionally colliding with Earth. Each of these events has the potential to alter our planet's environment dramatically, influencing everything from the atmosphere to the evolution of life itself. Learning about past impacts can help us understand our planet's resilience and vulnerability to cosmic events. By studying comets and asteroids, we are not just looking at individual celestial objects. We are uncovering the broader narrative of our solar system's history, including the origins of planetary bodies, the evolution of environments, and the enduring influence of celestial mechanics. Each finding plays a key role in piecing together the complex puzzle of our cosmic neighborhood. Spacecraft missions such as New Horizons are pivotal in unveiling the secrets of our outer solar system. By venturing to distant celestial bodies, New Horizons has provided a unique opportunity to study regions and objects that have remained largely unexplored. Think of it as sending a scientific scout to areas where our telescopes can't quite capture the full picture. Launched nearly a decade ago, New Horizons made headlines with its historic flyby of Pluto, revealing a world more complex than previously imagined. It showed us icy mountains, wide plains, and even possible weather patterns on a planet that was demoted from its planetary status. These findings challenged long-held assumptions and sparked further questions about the formation and evolution of the Kuiper Belt, a region beyond Neptune filled with icy bodies. Beyond Pluto, the mission continues to explore other distant objects, offering insight into the building blocks of our solar system. Each encounter with these distant worlds allows scientists to piece together how the solar system formed, including our own planet. The data collected provides invaluable information about the compositions, atmospheres, and potential for past or present activity on these distant moons and dwarf planets. Missions like New Horizons serve as time machines, looking back at the early solar system. By studying these distant objects up close, we not only learn how planetary systems evolve, but also gain a deeper understanding of the potential for life beyond Earth. The revelations from New Horizons are just the beginning. They set the stage for future explorations that will continue to reshape our understanding of the cosmos. Among the myriad of exoplanets discovered, some stand out due to their bizarre characteristics that challenge our understanding of planetary formation and conditions for life. One striking example is a planet known as hot Jupiter. This type of exoplanet resembles Jupiter in size but orbits extremely close to its star, resulting in scorching temperatures. The sheer contrast between a gas giant's size and its close proximity to a star raises intriguing questions about how such a planet could form in cooler areas of a solar system and migrate inward. Another fascinating find is an exoplanet dubbed Diamond Planet. This world is believed to contain an abundance of carbon, potentially crystallizing into diamond under the right conditions. The concept of a planet literally made of diamonds intrigues scientists not only because of the unexpected materials, but also due to what it implies about the diverse chemical processes in different planetary systems. Then there's an unusual planet that experiences extreme weather patterns, with temperatures hot enough to melt metals. The atmosphere of this planet is thought to have clouds made of molten glass, which could be blown by fierce winds. Its chaotic and hostile conditions challenge our traditional views of what constitutes a habitable environment and highlight the diversity of atmospheres that exist throughout the universe. Additionally, there are exoplanets that orbit two stars, known as circumbinary planets. These planets experience dual sunsets, creating a breathtakingly unique environment. Their existence raises questions about stability in such complex gravitational fields and whether life could survive under such extraordinary scenarios. What captivates scientists about these unusual exoplanets is not merely their exotic characteristics, but the broader implications of their existence. Each discovery forces researchers to reconsider the boundaries of planetary science, habitability, and the potential for diverse worlds beyond our own. These unusual planets broaden the horizons of our imagination and inspire deeper inquiries into the universe's workings. The transit and radial velocity methods have revolutionized our understanding of exoplanets, planets that orbit stars outside our solar system. The transit method involves observing the slight dimming of a star's light as a planet passes in front of it from our viewpoint. This tiny drop in brightness signifies that a planet is crossing the star's face. The amplitude and duration of this dimming provide vital information, such as the planet's size and orbital period. By knowing the star's brightness and the characteristics of the planet's transit, scientists can estimate key features including the planet's diameter and distance from its star. On the other hand, the radial velocity technique measures the star's movement in response to the gravitational tug of an orbiting planet. As a planet circles a star, it exerts a gravitational pull, causing the star to wobble ever so slightly. This wobble affects the star's light, shifting it toward the blue end of the spectrum as it moves closer and to the red as it drifts away. By analyzing these shifts, astronomers can deduce the planet's mass, orbital shape, and distance from the star. Together, these techniques paint a more complete picture of exoplanets. The transit method reveals potential habitability by determining the size of a planet and its position within the star's habitable zone, while the radial velocity provides insights into its mass, which influences factors like gravity and atmosphere. Continuous advances in technology enhance these methods, enabling discoveries of even smaller and more distant worlds. Ultimately, they allow us to explore the diversity of planetary systems, prompting fundamental questions about the formation of our own solar system and the potential for life beyond Earth. Proxima Centauri b is an intriguing target for future exploration because it is located just over 4 light-years away from our solar system, in the habitable zone of its star. This region is the perfect distance where conditions might allow liquid water to exist on the surface, which is essential for life as we know it. The planet's potential for exploration hinges on several factors, including its environment, atmosphere, and proximity. Scientists believe that Proxima Centauri b could have rocky characteristics, much like Earth, which opens up possibilities for discovering whether it has a stable atmosphere capable of supporting life. The star it orbits is a red dwarf, which means it emits less heat and light than our Sun. This lower energy output contributes to a unique climate on the planet, and examining its atmosphere could reveal whether it contains the right gases to support life. In particular, the presence of oxygen or methane could be significant indicators of biological activity. Moreover, the closeness of Proxima Centauri b means that future missions may not require the decades-long journeys that other targets could entail. Concepts for exploration often ponder advanced propulsion methods, such as light sails that could be propelled by powerful lasers, that might allow spacecraft to reach the planet within a reasonable time frame. These missions would focus not only on surveying the planet's surface, but also on analyzing its atmosphere and even searching for signs of life through remote sensing techniques. As we look to the future, Proxima Centauri b represents a fascinating opportunity for humanity. If we can overcome the technological challenges ahead, such a mission could deepen our understanding of other worlds and the potential for life beyond our solar system, making this distant planet a beacon of possibility in our quest for cosmic knowledge. The discovery of exoplanet atmospheres has profoundly shifted our perspective on what makes a planet potentially habitable. For many years, scientists focused primarily on locating planets that lay within the habitable zone, an area around a star where conditions might allow liquid water to exist. This was based on the assumption that if a planet was hot enough or cold enough, it could support life as we know it. However, the detection of exoplanet atmospheres has introduced a more nuanced understanding of habitability. An atmosphere can offer protection from harsh stellar radiation, regulate temperature through greenhouse effects, and even harbor essential chemicals for life. For instance, the presence of gases like oxygen or methane can indicate biological processes, while an atmosphere rich in carbon dioxide can suggest a planet retains heat, creating a stable environment. Moreover, scientists have utilized spectroscopic techniques to analyze the light that filters through an exoplanet's atmosphere during transits. This method lets them identify specific molecules, helping to determine the planet's composition and the processes occurring within its atmosphere. Discovering water vapor or complex organic molecules provides tantalizing clues about a planet's potential for life. Furthermore, the study of exoplanet atmospheres emphasizes that a planet's surface conditions alone may not tell the whole story. For example, a planet with a thick atmosphere might have surface temperatures that are inhospitable, while another with a thinner atmosphere could have the right conditions for liquid water. In this way, the atmosphere acts as a crucial mediator of habitability, transforming our search from merely identifying the right location to understanding the complex interplay of different environmental factors. Ultimately, these discoveries encourage scientists to think broadly about life's possibilities in the universe, considering a diverse range of planetary conditions that could support life, rather than limiting their search to Earth-like scenarios. This deepens our exploration into the unknown, revealing that habitability may be more common in the cosmos than previously thought. Detecting signs of life on exoplanets is a challenge that requires significant advancements across multiple fronts. First and foremost, we need more powerful telescopes capable of observing distant worlds. Current telescopes can identify exoplanets but struggle to study their atmospheres in detail. Enhanced observing technologies, particularly space-based ones, can help capture the faint light that filters through an exoplanet's atmosphere, revealing the chemicals present. Next, advancements in spectroscopy are crucial. This technique allows scientists to analyze light from distant planets to determine their atmospheric composition. Finding specific molecules, such as oxygen or methane, could indicate biological processes. The ability to analyze light across a wide range of wavelengths improves our chances of identifying molecules that may signify life. Additionally, fostering international collaboration and pooling resources to develop new missions will accelerate our research. Projects that combine efforts from multiple nations can leverage different technologies and expertise to create telescopes and instruments that can penetrate deeper into space. Another area needing enhancement is the development of artificial intelligence and machine learning. These technologies can assist in filtering through vast amounts of data, identifying patterns that may suggest biological signatures more efficiently than human analysis alone. Moreover, continued research into understanding the conditions necessary for life on Earth and the potential forms it may take on other planets is vital. This knowledge will guide our search, focusing on environments that are more likely to host life, such as planets located in their star's habitable zone where conditions might be just right for liquid water to exist. Finally, long-term sustainability and funding for these ambitious projects will ensure that the scientific community can pursue these pioneering endeavors. By creating supportive frameworks for research and exploration, we can pave the way for breakthroughs in our quest to uncover whether we are alone in the universe. Each of these advancements is a stepping stone toward the ultimate goal of confirming the existence of life beyond our own planet. Galactic archaeology is a fascinating field that helps us unlock the secrets of our galaxy's history, much like traditional archaeology reveals the past of human civilizations. Imagine the Milky Way as a giant time capsule, filled with stars, gas, and dust that carry the stories of their origins and interactions. By studying the chemical compositions, movements, and ages of stars, scientists can piece together the tale of our galaxy's evolution. As each star forms, it incorporates elements from the surrounding material, creating a fingerprint that reflects the conditions of the early universe and the processes that have shaped its environment over billions of years. By analyzing the lighter elements produced in the earliest stars alongside heavier elements forged in later generations, researchers can establish when and how different parts of the galaxy formed. The movement of stars throughout the Milky Way also provides crucial information. Some stars travel through our galaxy on erratic orbits, suggesting that they originated from other galaxies or were influenced by galactic events like mergers. By mapping these pathways, scientists can reconstruct past interactions between the Milky Way and its neighboring galaxies, revealing a dynamic history of growth through accretion and collisions. Furthermore, very old stars, often found in the halo of our galaxy, serve as witnesses to events that occurred early in the galaxy's formation. These ancient celestial bodies can tell us about the conditions in the early universe and the formation of the Milky Way itself. Galactic archaeology allows us to decipher the narrative of the Milky Way, providing insights into its formation, structure, and the processes that formed the diverse array of stars, stellar remnants, and planetary systems we observe today. Each discovery deepens our understanding of not only our galaxy, but also the larger cosmic history to which it belongs. The chemical compositions of stars serve as essential clues in unraveling the history of galaxies. When stars form, they accumulate elements from the gas and dust present in their surroundings. As these stars go through their life cycles, they undergo nuclear fusion in their cores, creating heavier elements. Eventually, many of these stars explode in supernova events, scattering their enriched materials back into space. This process seeds the interstellar medium with a diverse array of elements, which can later be incorporated into new stars and planets. By studying the chemical makeup of different stars in a galaxy, scientists can trace the timeline of element creation and distribution. Each generation of stars contributes uniquely to the chemical inventory. For instance, the oldest stars, which are often metal-poor, indicate that they formed from primordial material primarily composed of hydrogen and helium, the first elements created after the Big Bang. In contrast, younger stars that contain higher levels of heavier elements suggest that they formed from gas clouds enriched by the supernovae of earlier generations. This stellar chemistry allows researchers to map out the evolution of galaxies. By observing which elements are abundant and how these vary across different regions, scientists can infer the processes of star formation, the frequency of supernova explosions, and even the interaction between galaxies. Analyzing the light spectra of stars reveals their chemical signatures, painting a picture of how galaxies have evolved over billions of years. Thus, the chemical compositions of stars act like the fingerprints of galactic history, offering a window into the past that helps us understand the intricate story of the universe's development. The history of the Milky Way galaxy is a tale woven from many mysterious threads, especially concerning its interactions and mergers with other galaxies. Imagine the cosmos as a vast dance floor where galaxies frequently glide toward one another, sometimes colliding or merging in spectacular ways. This merging process profoundly shapes their structures and histories. One of the greatest mysteries involves understanding the full impact of these collisions on the Milky Way's formation. Throughout its life, the Milky Way has absorbed smaller galaxies, reshaping its structure and contributing to the starry tapestry we see today. These smaller galaxies serve as building blocks, providing fresh material for star formation and altering the galaxy's dynamics through gravitational interactions. However, the precise number and identity of these merging companions remain largely unknown, leaving gaps in our understanding of our galaxy's past. Moreover, each merger generates complex gravitational waves and triggers bursts of star formation. As gas and dust from the merging galaxies collide, they can lead to the birth of new stars in regions previously quiet. Yet, not all merging events are harmonious. Some can disrupt stellar orbits and produce chaotic distributions of stars and other matter. The distinctive halo of stars surrounding the Milky Way, for instance, provides clues to its turbulent history, hinting at past encounters that still influence the galaxy's behavior today. Another intriguing aspect is the possibility of dark matter, an elusive substance that makes up a significant portion of the universe's mass, playing a role during these mergers. As galaxies collide and merge, they interact not just through visible matter but through dark matter too. Investigating how these interactions shape the distribution of dark matter in and around the Milky Way could unlock secrets about both our galaxy and the universe at large. The Milky Way's past is also closely related to understanding the fate of our galaxy. Future projections indicate a looming merger with the nearby Andromeda galaxy. This is a slow-motion cosmic encounter, anticipated to occur several billion years from now. As we study past mergers, we gain insights into what is to come, though the exact details of such an event remain cloaked in uncertainty. The merging history of the Milky Way is a complex narrative filled with intriguing questions and ongoing research. Each revelation brings us closer to understanding how our galaxy evolved into the magnificent structure we inhabit today, and hints at the cosmic ballet that will continue far into the future. Star clusters are like time capsules in the universe, providing astronomers with invaluable insights into the history and evolution of galaxies. These clusters come in two main types: open clusters, which are loosely bound groups of young stars located in the spiral arms of galaxies, and globular clusters, which are densely packed spheres of older stars that orbit the core of galaxies. The age of a star cluster can reveal the time period in which the stars formed, acting like a snapshot of cosmic history. For instance, globular clusters are thought to be some of the oldest remnants from the early universe, containing stars that formed when the universe was relatively young. By studying these ancient stars, scientists can learn about the conditions that prevailed in the early phases of galactic evolution. Moreover, the composition of stars within clusters tells us about the material available at the time of their formation. Newer stars in open clusters often contain heavier elements formed from previous generations of stars, while the older stars in globular clusters are typically deficient in these heavier elements. This variation highlights the processes of stellar evolution and the recycling of materials in galaxies. The distribution and dynamics of star clusters also provide clues about how galaxies formed and grew. For example, observing how clusters are spread out can inform researchers about the gravitational interactions within a galaxy. By analyzing the movements of these clusters, scientists can infer the presence of dark matter, the unseen mass that influences how galaxies behave. Star clusters are cosmic fossils that encapsulate different stages of galactic evolution. They not only reveal the ages and compositions of their stars, but also reflect the larger processes that have shaped galaxies over billions of years. Through these stellar groups, we can piece together the dynamic story of our universe. As we look to the future of galactic archaeology, several instruments and missions stand out as essential tools that will deepen our understanding of the universe's history. One of the most promising developments is the next generation of space telescopes. These telescopes are designed to peer deeper into the cosmos than ever before. With advanced optics and sensitivity, they will be able to analyze the light from ancient stars and galaxies, revealing clues about their formation and the early conditions of the universe. Another critical advancement comes from missions focused on surveying our own galaxy, the Milky Way. Upcoming missions that utilize precise measurements of star positions and motions will provide insights into the distribution of stars and their chemical compositions. This data helps reconstruct the history of our galaxy's formation and growth over billions of years. By understanding the patterns of stellar evolution, astronomers can piece together the events that shaped the Milky Way. In addition to telescopes, innovative instrumentation on board space probes is equally important. These probes can capture and analyze cosmic dust and gas, offering detailed information about the building blocks of galaxies. The collected data can help scientists understand the processes that led to star formation and the evolution of galaxies themselves. Furthermore, advancements in computer simulations and artificial intelligence are becoming invaluable. Sophisticated models allow researchers to simulate galactic evolution, testing hypotheses about how galaxies form and interact over cosmic time. By comparing these simulations with real observational data gathered from telescopes and missions, we can refine our understanding of the universe's history. Collaborative efforts across global projects, such as large-scale sky surveys, will also play a crucial role. These initiatives combine observations from multiple sources, providing a comprehensive view of our galaxy and beyond. The upcoming surveys promise to identify and catalog millions of stars, revealing hidden structures and the influences of dark matter on galactic formation. The future of galactic archaeology relies on a combination of advanced telescopes, space probes, innovative computing methods, and collaborative surveys. Together, these tools will allow us to unlock the secrets of galaxy formation and evolution, providing a fascinating glimpse into the cosmic past. Cosmic constants are key quantities that play essential roles in determining the behavior and structure of the universe. Think of them as the foundational principles that govern how everything, from the smallest particles to the vast expanses of galaxies, interacts with one another. Among the most notable of these is the gravitational constant, which outlines the strength of gravity, influencing how objects attract one another across great distances. Another important constant is the speed of light, a value that not only represents how fast light travels, but also serves as a limit for all information and matter within the universe. It forms the backbone of Einstein's theory of relativity, shaping our understanding of time, space, and their interconnectedness. There are also constants related to the forces that define fundamental interactions in nature, such as the electromagnetic force and the weak nuclear force. These constants help us understand processes like how atoms bond and how stars generate energy through nuclear fusion. The significance of these cosmic constants cannot be overstated. They provide the rules by which the universe operates. Without them, the structure and evolution of matter, the formation of stars and galaxies, and even the processes that allow life to exist would not be possible. Essentially, they are like the instructions in a recipe, ensuring that the ingredients of our expansive cosmos come together in a harmonious way. The cosmos, as we observe it, operates under the assumption that certain physical constants remain unchanged throughout the universe. These constants, like the strength of gravity or the speed of light, are the foundational pillars upon which our understanding of everything from stars to galaxies rests. However, variations in these cosmic constants challenge the notion of a uniform universe in a profound way. When researchers discover evidence that these constants might not be constant at all, it suggests that the fundamental rules governing the universe could alter depending on where you are or when you look. Imagine a game where the rules change from one region of the playing field to another. Suddenly, the predictability that scientists have relied on for decades is thrown into question. It presents a reality where local conditions can dramatically alter physical outcomes, leading to different forms of matter, energy behaviors, and even cosmic structures. For example, consider the implications of a weaker gravitational force in some regions of the universe. This would influence the formation of galaxies and stars, potentially allowing them to behave differently based on their environment. Such variations could mean that some galaxies might form robustly, while others could struggle to maintain their structure, leading to a diverse cosmic landscape that contradicts our established models of cosmic uniformity. Moreover, this notion extends to theories regarding the Big Bang and cosmic inflation, the rapid expansion of the universe following its inception. If constants fluctuated during this critical period, models of how the universe evolved would require significant revision. It raises questions about the very origins of cosmic phenomena, suggesting that our understanding of beginnings is far more complex than a single uniform event. These challenges compel scientists to explore alternative frameworks and theories. The pursuit of answers requires a re-evaluation of everything we thought we knew about the universe. It's a reminder of the dynamic and ever-evolving nature of scientific inquiry, where each discovery can lead us to redefine foundational concepts and expand our understanding of a universe that is more intricate than we could have ever imagined. Constants like the speed of light and Newton's gravitational constant are fundamental to our understanding of the universe. The speed of light, for instance, is the ultimate speed limit of the cosmos. It represents how quickly information and matter can travel through space. This constant not only governs the way we perceive time and distance, but also shapes our understanding of relativity, asserting that time behaves differently based on the relative speeds of observers. When we say that nothing can exceed the speed of light, we are acknowledging an essential boundary that influences the behavior of all energy and mass in the universe. On the other hand, Newton's gravitational constant serves as the backbone of our gravitational interactions. This constant determines the strength of gravity between objects based on their masses and the distance separating them. It's an essential factor that allows us to describe the orbits of planets, the movements of galaxies, and the formation of cosmic structures. Without it, our grasp of celestial mechanics would unravel, making it impossible to predict the motion of everything from falling apples to distant stars. Together, these constants anchor the laws of physics, providing a consistent framework that underlies the behaviors of the universe. They are the rules of the cosmic game, shaping interactions on both an astronomical scale, such as galaxy formation, and at the level of individual particles. Through these constants, we gain insight into the very fabric of reality, allowing scientists to explore and make sense of the intricate dance of celestial bodies and the forces that bind them. Cosmic constants are like the hidden threads weaving together the fabric of our universe, yet they remain shrouded in enigma. These constants, such as the speed of light, the gravitational constant, and the fine structure constant, govern the fundamental interactions between particles and the behavior of everything from atoms to galaxies. Despite their critical importance, many questions linger about why these values are what they are and how they were determined. One of the central mysteries revolves around the fine structure constant, which influences the strength of electromagnetic interactions. This constant plays a key role in determining the stability of atoms, yet scientists cannot fully explain why it takes its particular value. Theories abound, from those suggesting connections to higher dimensions to others, positing a deeper order in physics yet to be discovered. Additionally, the gravitational constant, a measure of the strength of gravity, remains perplexing. Its value appears finely tuned to enable the formation of stars and galaxies. However, our understanding of how this constant interacts with quantum mechanics is incomplete. If gravity is as fundamental as we believe, why is its value drastically different from other forces? Moreover, cosmic inflation, the rapid expansion of the universe after the Big Bang, raises further questions about these constants. As the universe expanded, the initial conditions favoring them could have led to various outcomes, which makes some scientists wonder if our universe is just one of many, each with differing constants in a vast multiverse. Ultimately, the quest to understand these cosmic constants teaches us about the universe's structure and evolution while reminding us how much we still have to learn. As we develop more sophisticated tools and technologies, the secrets hidden within these constants may one day emerge, potentially leading to groundbreaking revelations about the nature of reality itself. The cosmic constants are fundamental quantities that govern the behavior of the universe, such as the speed of light and the gravitational constant. A deeper understanding of these constants could be revolutionary for theoretical physics, much like finding the missing pieces of a complex puzzle. If scientists discover that one or more of these constants can vary under certain conditions, it would challenge our current understanding of physics as a fixed framework. For instance, imagine if the forces of nature, like gravity or electromagnetism, were not constant throughout the universe but fluctuated depending on location or time. This realization would lead to a re-evaluation of established theories, such as general relativity and quantum mechanics, and could fuel the development of a unified theory that elegantly ties together all forces. Furthermore, a refined understanding of these constants could help explain why our universe seems fine-tuned for the existence of life. The very balance in the values of these constants allows matter to exist, stars to form, and galaxies to evolve. Discovering deeper connections between them could illuminate the conditions necessary for life and broaden our search for it elsewhere in the cosmos. As researchers delve into the mysteries of cosmic expansion, dark energy, and dark matter, any revelations about these constants may lead to groundbreaking insights. Such findings could not only advance theoretical physics, but also shape our understanding of the cosmos, offering new ways to conceive of everything from black holes to the Big Bang itself. A deeper grasp of these fundamental principles could be the key to unlocking the secrets of the universe, bringing us closer to answering profound questions about existence and the nature of reality. Time dilation is a fascinating phenomenon where time does not tick at the same rate for everyone. It can stretch and contract depending on speed and gravitational influence. Imagine time as a fabric that can bend and warp. In the realm of high speeds, especially as you approach the speed of light, that fabric stretches. For someone moving incredibly fast, like an astronaut traveling in a spacecraft, time for that individual would actually pass more slowly compared to someone remaining still on Earth. This means when the astronaut returns, they would have aged less than their friends and family, a consequence of their high-speed journey. Now consider gravity. When you're near a massive object, such as a planet or a star, the gravitational field is stronger. This immense gravity can also warp the fabric of time. The closer an object is to a massive body, the slower time goes for it relative to someone further away. For instance, if someone were to stand on the surface of a black hole, which exerts a tremendous gravitational pull, they would experience time at a much slower rate than someone safely far from its reach. Together, these effects create a universe where time is not a universal constant. It is dynamic and influenced by both speed and gravity, challenging our perception of time as a steady, unchanging line. This means that time can stretch in space travel and bend under the weight of gravity, fundamentally affecting how we understand existence and experience. The theory of relativity, developed by Albert Einstein, reshapes our understanding of time and space. At the core of this theory is the idea that time is not a constant, but rather can change depending on speed and gravitational influence. For astronauts traveling in space, particularly those moving at significant fractions of the speed of light or living in different gravitational environments, time behaves differently than it does on Earth. As astronauts move swiftly through space, time for them passes more slowly compared to people on Earth. This effect is known as time dilation. Imagine a clock on a spaceship zooming away from Earth. That clock ticks at a slower rate relative to a clock on the planet's surface. The faster the spaceship travels, the more pronounced this effect becomes. Consequently, if an astronaut spends time in a high-speed spacecraft, they could return to Earth having aged slightly less than their counterparts who remained on the planet. Additionally, the influence of gravity also plays a critical role. Einstein proposed that massive objects like planets and stars warp the fabric of space and time around them. This means that the closer something is to a massive body, the slower time moves compared to a location that is farther away. For example, an astronaut on the International Space Station, which orbits Earth and experiences less gravitational pull than someone on the surface, will perceive time passing just a bit faster than those on ground level. Together, these aspects of relativity create fascinating scenarios for astronauts, showing that their journey through the stars could mean they experience time differently than those of us on Earth. A profound reminder of the complex relationship between motion, gravity, and the nature of time itself. Time dilation, a fascinating consequence of Einstein's theory of relativity, has been demonstrated through various experiments on our planet and in outer space. One of the earliest and most famous tests involved high-speed particles. Scientists used a particle accelerator to create a type of particle called a muon. These muons are unstable and should decay relatively quickly when at rest. However, when they travel at speeds close to that of light, their lifespan appears to stretch, allowing them to be detected longer than expected. This effect vividly illustrates how high speeds can drastically alter the perception of time. On Earth, another notable experiment involved precise atomic clocks. Two highly accurate clocks were synchronized and set to the same time. One clock remained stationary on the ground, while the other was flown around the world aboard an aircraft. Upon completing the journey, scientists found that the clock on the aircraft measured less time compared to the stationary clock. This discrepancy perfectly aligned with predictions made by relativity, demonstrating how motion can affect time perception. In space, the effects of time dilation have been confirmed with even more sophisticated technology. One significant experiment utilized satellites in Earth's orbit. These satellites carry atomic clocks similar to those used on the ground. Because they are moving rapidly and experience a different gravitational field, their clocks tick at a slightly different rate compared to clocks on Earth. The data collected from these satellites, particularly from the Global Positioning System, requires constant adjustments to account for this time difference to ensure precise navigation. Each of these experiments reinforces the idea that time is not a universally constant experience, but rather something that can stretch and fluctuate based on speed and gravitational influence. This insight fundamentally changes our understanding of the universe and our journey through it. Time dilation presents a fascinating interplay of challenges and opportunities that could significantly impact future space travel. At its core, time dilation occurs due to the effects of speed and gravity, altering the passage of time for travelers based on their relative motion to others. Picture two identical clocks. One remains on Earth while the other journeys through space at a significant fraction of the speed of light. For those on Earth, time passes normally, but for the spacecraft traveler, time will seem to slow down. This means that while a few years may pass for the astronaut, many more years could have elapsed back on our planet. This phenomenon creates a unique challenge for long-duration space missions. As humans venture farther into the cosmos, they risk experiencing time differently than those remaining on Earth. This leads to emotional and social consequences, as relationships and societal structures could dramatically change during long voyages. For example, what might feel like a brief journey for the crew could turn into decades or centuries for their loved ones, complicating the dynamics of space exploration and home life. On the flip side, time dilation also opens doors to incredible opportunities. The ability to travel at high velocities not only allows for quicker journeys across the vast expanse of space, but also makes interstellar exploration feasible within a human lifetime with the right technology. If we can harness advanced propulsion methods like those hinted at by theories of relativity, we could potentially explore distant stars and galaxies in a time frame that makes future exploration projects more palatable and realistic. Moreover, understanding time dilation could enhance our approach to mission planning and crew management. By accounting for these effects, space agencies could design missions that mitigate the emotional toll on astronauts and ensure the successful reintegration of space travelers when they return home. Thus, While time dilation brings with it certain difficulties, it also propels our ambition to venture further into the universe, transforming potential limits into tantalizing goals for humanity's future in space. The concept of relativistic time travel raises fascinating questions that intertwine philosophy and practicality. At its core, relativistic time travel stems from the principles of Einstein's theory of relativity, which suggests that time is not a constant. Instead, it behaves like a flexible fabric that can stretch or contract depending on speed and gravity. This leads to the intriguing idea that if we travel at speeds close to that of light, we could experience time at a dramatically different rate than those who remain stationary. Philosophically, this notion challenges our understanding of reality and existence. It invites us to ponder the nature of time itself. For instance, if one could travel into the future by moving at incredible speeds, what does that say about our experiences and memories? Does the future become accessible in a tangible way, or does it merely highlight the limitations of human perception? Additionally, such travel could evoke ethical considerations regarding free will and the potential to alter one's own timeline or the timelines of others. The paradoxes created by altering past events prompt deep reflection on causality, fate, and the moral responsibilities that accompany such power. Practically, the idea of traveling through time as portrayed in science fiction encounters significant challenges. Achieving the velocities necessary for relativistic time travel is currently beyond our technological capabilities. Furthermore, the extreme conditions, such as the intense energies or forces required, pose risks that we are not equipped to handle. Even if we could reach such speeds, the implications for human biology become complex. Time dilation means returning to a world that has significantly aged, leaving time travelers isolated from their original context. The combination of these philosophical inquiries and practical hurdles showcases the rich complexity of relativistic time travel. While it inspires imaginations and fuels theoretical exploration, it remains a profound reminder of how little we truly understand about time and the universe. In contemplating time travel, we not only engage with the boundaries of scientific inquiry, but also the deeper questions about our place within the continuum of existence.